So I will highlight the most important part of that, because the other presentation will be do the deep dive in the what we achieved in this project. So that's why I just try to summarize it. So that, okay, the EU goals. So I summarize it a little bit other way. So the main goal of the EU, in my view, that they would like to use the data centers as a boiler. So that is the most simplest thing. So we have the huge amount of data centers generating heat, and we would like to use it as a boiler. And the other is that we have to use it in the tertiary building. So that is the main aim. And the EU goals is for us that give us the possibility to explore how can we do this vision possible. So that's the main task of this project. We have to check all the parts of this ecosystem, and as we checked it, we have to see what kind of barriers we have, and that's we have to give the answer for the European Union and all the stakeholders who is involved in this marriage, we can say. So we would like to have these two components of this system, the data centers, the server rooms owners, and the buildings to connect their assets together. But currently this is not working. What is the challenges? That EU directives, you heard from Attila that we have huge amount of EU directives and targets, but we can see that it's not working currently. So nobody would like to connect the assets. But we have to work on it to check that. Is it technically feasible, what European Union wants on the assets owner, and economically viable? So if it's not a business, it has not good results, when we put together the assets, nobody would like to do it. So we can have some very special sentences, we can say, or special laws about what to do, but without the business interest, nothing will happen, or that will not cause huge impact. So that's why we have to overcome this barrier. That's about the project. We have to check what are these things. So that's what is the project path, because I have to give you the overview of the project. So that's why I go a little bit in the details. So in the beginning, in every this type of project, we have to collect all the data, and we have to check all the possible way how to build from this data some special models, and for modeling everything what we can do about these targets. And we have to check always what kind of barriers, what we can find when we do our projects. So, and this is the structure of what we do in this project. You can see that we started with the planning phase, we closed it down, and then there is a project execution and management task force continuously, which managing all the other tasks. And we have the other one, which is very important, that is VP10, it's just about the communication. So when we achieved any type of achievement in our project, we have to communicate to you constantly, so you can follow our achievement on the web. And you can see the other packages, which is very important for reaching our target. So, and just some highlight of these work packages. So we are working in work packages, and they are connected together. As you can see in the previous slides, this is a specialized structure. We can create the data to the next stage and the achievements. So the work package 3 is about the energy performance and waste heat. So the leader of this work package is Aalborg University, and they are working with the historical data. And as Attila mentioned, we have 5 places when we have pilot projects. So they collect the data from the pilot projects, and doing the, for example, optimization suggestions about what can we do in this situation. So they checking all the possible things about the data centers and the buildings on the asset view, on the data view. And if we check the technical validation, and that is the DS Tech, so they are creating special models. So the big achievement from the DS Tech is that they can simulate what's happening inside the data center. And they propose some very special changes in the existing data centers, which is in the pilot. That's connected with the pilots. So that gives the aim to how can we increase the waste heat, for example, waste heat, the temperature, and how can we put out more heat from the system. So that's about it. And this is a very special one, because to reach this goal, what the EU would like to put onto the market, that is, how can we capture more and more heat, more efficient way, and this is the solution, one of the solutions how we can do that. That is the hybrid cooling. So when we use the liquid cooling and the air cooling together to maximize the heat what we can pull out from the system, from the data sensor. And what is very important for everything when we do any kind of planning, or that is, we need some special tool for modeling everything what we like to modify or creating with existing or future data centers. So that's why this holistic data center management and data twin is this is one of the essential tools which you have to use. But all of this, you will receive some information about the presentation what will be held after me. So, and if we can, when we created the architecture of the new type of, or the modification of the data center, and we build it, so we need the system what can handle in the right way the system what we created. So that's why the multi-objective energy management system is important for put these things in operation at the data center level and the building level. So, and this is a self-assessment tool, and the self-assessment tool could give some insight, what can we change in the system to work it much better. And it could be earlier, and then it's when the system is operated. And this is the work package I'm leading. I think this is one of the most important part, because we have to calculate that things what is important for the asset managers or the owner of these facilities or buildings, because we have to concentrate here for the biggest heat generator, that is the data center itself. So we are in that building what we are what we will how can I tell you to so what we will measure and counting and proposing what can we do with this TRNSYS data center. And the other is that there is a need from the European Union to use renewable energy. So that the other topic is here to how can we use the renewable energy to feed the data centers and the buildings. And one of the most important parts is that we have to create special configuration portfolio, at least 6 types of tertiary building. And from this, we have to set up, and with the model what the others created for us, we have to create business cases. So we have to exactly show to the possible future customer that, okay, if you would like to make your decision on this level, that would be the result of your decision, because we can give them the insight if they give us some major data about their data center, and on the other side on the buildings, we can calculate what will be the result of the marriage, if we can say this way. So, and we have to create some white paper where we can give the recommendation to the union, and of course for the asset managers, and we have to give some special design support for the engineers who have to do this engineering part. So currently, there is not exist this models in this type of engineering tool. So that's why we will create some special libraries for doing this activity better. And of course, when the system is created, the decision made and the system created, we have to give this, an operation tool for operating the system, the data center and the building together. And the other side, that's what I mentioned earlier, that we have to create some calculators about that, what it can the estimated potential savings of the cost if we do these things together, and how can we make some decision support to make it happen, all the things that make it happen. So I heard that I don't have too much for that. So you will receive some detailed information on the upcoming presentation. So that will be the menu for today, and you will receive much more information. Thank you for your attention.
As Attila said, my name is Rasmus Jensen. I'm an associate professor at Aalborg University in Denmark. our main focus is on buildings, so building operation, building design, building management. So this presentation is done together with my colleague Simon, who's sitting in the back, and also with the help of EMPA, Binod and his team. And what we tried to do here was to forget a little bit about data centers and then try to look at the buildings to see what is actually possible to reuse in buildings, heat, and mainly what temperature levels do we require. Of course, if you connect to district heating, depending on where you are in the EU, it might be 70, 80, 90, 100 plus degrees. So does this actually correspond to what is needed in the buildings? So that's what we tried to set out to describe by analyzing measurements from different buildings. So we looked at this building where we are currently sitting. So it's a university building. We have laboratories, we have office for staff, we have lecture rooms and student group rooms, roughly 150 employees and 600 students in this building, 9,000 square meters. If we look at the HVAC systems, we have 9 ventilation units, all with heat recovery, 5 different heating systems. We have domestic hot water production with heat exchangers, so no storage tanks. We have 3 cooling units, and it's equipped with a Schneider BMS system, logging and controlling the different things. So just before we dive into some of the results, please remember that no 2 buildings are alike. So buildings can be very different in terms of their energy need, insulation level, HVAC systems, user profiles, and also designed for very different heating systems. So when you have a specific building and you want to utilize waste heat, you always have to do a kind of in-depth analysis of what is this particular building demand and requirements. So when we look at waste heat potential of buildings, it depends on how we connect it. So there are different places in the building where we can connect the waste heat. So we can go at the main system. That would be the easiest. So where the district heating comes into the building or where you have your boiler, if we connect there, very easy, not much plumbing. But we might also be able to have, you could say, a special plumbing for all the HVAC systems categories. Could be the ventilation systems, could be the heating systems, domestic hot water, or we could actually attack on the individual systems. So right here at the heat exchanger for domestic hot water, or right here at the heat surface for the ventilation system. And that gives us different possibilities of reusing heat with lower temperatures. So we tried to show it here on the schematics. So we have district heating coming into the building. So we can measure either here at T3. So what is the temperature of the district heating coming into the building? We can measure somewhere out in the building, and we can measure just before we have the heating coil in the ventilation system. And what you can see here is that there is it's a little bit difficult to see, but you can see some black spots, and there are some red spots. So that's the temperatures here of T3 and T2, going up to almost 90 degrees, typically above 60. There are some small part of the time where it's lower. But if we track the individual system, the blue one, we can see that we are 20 is probably when it's not running. It's only running in you could say in during daytime. But typically we have temperature needs of around 25, 40 degrees for the ventilation system. So it's quite different temperatures that is required depending on where we sort of connect our waste heat to the building systems. Here it's divided into domestic hot water and ventilation. So domestic hot water is fairly uniform temperature levels because we need to secure a safe temperature levels in the domestic hot water to avoid Legionella. So it's around 50 degrees. So we are typically around 50 degrees all year round for the energy we need for domestic hot water. So if you have water of 55 degrees, 60 degrees would be very good for this. If we look at the ventilation, we have 2 different ventilation systems here, running between 20 and 40 degrees, and between 25 and up to almost 60 degrees. So again, quite low temperatures compared to what we have when we look at the temperatures coming into the building from the district heating network. We also looked at a very interesting, fancy building at EMPA that was designed with very low energy use in mind, and also taking into consideration that we would like to design a building that were able to utilize as much waste heat as possible. So the building at Aalborg University is just a standard office building, 10 years old. So for Danish conditions, it's not state of the art, it's completely standard, maybe even a bit less than standard. But the buildings that is analyzed here at EMPA is quite unique, and you can also see here that if we take, it's divided into 2 different units, different apartments or part of the building. And you can see temperatures here for the ventilation and the heating between 22 and 28 degrees for the heating, and ventilation is 28 up until 24. So really, really low temperatures and huge potential for using the waste heat. And you can see the same down here. If we have 30 degrees, we can almost cover everything. So if we try to summarize for the findings for the buildings that we have analyzed, and of course also what we see in many buildings in Denmark, ventilation normally never above 50. Also because if you heat up the air more than 53, you start sort of burning the dust and you get a bad smell. So for many reasons, you would not like to go that high. Typically 25 to 35 degrees and rarely above 40. If we have floor heating, low temperatures, 25, 35, that's what you saw in the EMPA case. You can, of course, have higher temperatures, but typically there is no need if you have a sufficiently insulated building. Radiators, typically in Danish conditions, 40 to 65. That may depend very much when your building was erected. Also, if we go back to, you could say, 50-year-old or older buildings in Denmark, it's typically designed for maybe 90 degrees, right? So it also depends on the age of the building and the heating system. But typically, even if you have an old building, a lot of them has been renovated. They have gotten new windows, maybe more insulation and so on, so they might actually be able to run on significantly lower temperatures. Domestic hot water, 45 to 65, and as long as we need to avoid Legionella, there's not much to do about the temperature levels there. Then we tried to divide it into for our building into how much are we using for heating, how much for ventilation, domestic hot water, and miscellaneous. So that would typically be the entrance door where you have the carousel with heating carpet and so on. And then we tried to divide it into different temperature sets so you can see how much you can cover of the energy needed for ventilation, heating, domestic hot water, depending on the temperatures. And we see that more than 80% of the heat can be substituted by waste heat from data centers. And of course, when you start digging into buildings, there is always faults that you discover. And we also did it in this case. So the very high temperatures for ventilation are due to a malfunctioning mixing valve, meaning that this was what we measured coming into the ventilation system, but it was not necessary. It was just a faulty valve. So this part here is not necessary. But you will encounter that when you go out in buildings, that there are always something that doesn't work according to plan. So what to do when your data center produces more heat than the building needs? Best way, of course, is to sell to the district heating network. If you can do that, that would be very nice. Or you can actually also use the building as a heat sink. So we will try out different strategies, different scenarios to utilize more heat than the building actually needs, right? So typically in buildings, we're focusing on running them as efficient as possible, but there's actually no problem in using more energy than absolutely strictly necessary. And in that case, the building can be used as a heat sink for the data center. So of course, if you have a storage tank, you can charge it. There are some running systems. We can be running systems in a way that increases the heat energy need. I will give an example of that in a while. We can dump heat through HVAC systems instead of a dedicating cooling unit. Typically, we don't do that, but in principle, you could mount a heating surface in the extract of the ventilation and just heat up the extracted air before you throw it out, just the way as you do with a dry cooler. So might as well just use the ventilation you already have as a dry cooler. We could also increase maybe the temperature in the buildings. Often people becomes happy in winter if it's just a little bit warmer. And all of these scenarios, they have potential side effects. We might need to increase electricity use. We might need to increase the cooling need, and we might decrease the quality of the indoor environment. But if we do it quite intelligent, we might also actually increase the quality of the indoor environment. We might decrease electricity use and cooling need. So there are possibilities of trying to think of operating buildings differently to try to act as a heat sink for the data center. And at least to us, that's a sort of a new way of thinking. Now we have too much energy, how to operate the building. So this is the energy profile of the building, and you can see we have quite many hours where we don't need much heat in the building. And that's where you either sell to the district heating or you use the building as a heat sink. And then we have this area that is probably where you would be aiming at to try to cover. And then there are, of course, a few hours where it's very cold and we need a lot of heating. Then if we look into the operation of one ventilation system, the blue line is the heating coil power. So for 3,000 hours of the year, we don't need any heating to supply the inlet temperature at the desired level. And then we have some hours where we need energy, and then there's some peak here at the end that we typically don't care much about. But a simple way of increasing the heat need is to stop running the heat exchanger. And that's what this orange curve is about. So if we stop running the heat exchanger, which we normally do to save energy, then we can easily take this whole area and use as a heat sink for the data center. So again, some possibilities of doing that. And again, there are hours where it's not directly possible to use the system as they are as a heat sink. So in conclusion, we have a huge potential to use waste heat from data centers, especially if connected to the individual HVAC systems to get the required temperatures down. And if you want to evaluate the potential of building, you need to measure at the individual systems. So after the mixing loop, if you want to have, you could say, really low temperatures. And try to investigate the building as a heat sink, even when there is no need for heating, in order to reduce, you could say, the cost for the cooling system of the data center. So the more you can use the building, the less you have to pay for cooling your data center. Yes, thank you.
Hi, so as Attila said, I'm Lilach Bushmitz. I'm a product director at ZutaCore, and today I'm going to explain a bit about two-phase direct-to-chip liquid cooling. So ZutaCore has developed a very unique technology that is based on a phase change of the electric liquid from liquid to vapor, and then condensing the vapor back to liquid, and this process removes the heat away from the processor. Through this technology, you can gain a lot of benefits, like high thermal design power support, efficient cooling at any climate. Heat reuse, of course, this is the reason we are participating in this project, and many more. I'm going to give more details later on. So why is it needed? So as you all know, the demand for computing resources and data are increasing rapidly. And the AI rise, of course, is moving this trend in further and faster than it used to be. So in order to meet this demand, the manufacturer, the processor developer and manufacturer, has to develop a more powerful chips that dissipate, that creates a lot of heat that needs to be removed. You can see on the right, yeah, the trend of the different chips. The yellow line is NVIDIA, the blue line is AMD, and the black and red is Intel. So you can see the trend is really increasing rapidly. Nowadays, most of the data centers are still being cooled by air. This is very challenging and probably won't be able to support the all the GPUs. The drawbacks of this system is going to be, it's going to consume a lot of energy, it's going to cost a lot of money, and it will pose a lot of environmental issues such as water usage and all the green gas emission. So another cooling solution needs to be provided. So liquid cooling technologies are becoming more and more interesting for this market. Liquid cooling technology include cold plates that are placed directly above the major heat source, which is the processor, and liquid inside the cold plates are absorbing the heat and remove it away from the chip. And the other technology is immersion, where you immerse a complete server in a liquid, in a dielectric liquid. The whole server is being immersed inside. The major drawback of the immersion is that you need to have a completely different infrastructure for this purpose. And another thing is because of each and every part of the server is being in touch with the electric liquid, it has to be material compatible to this liquid. And the major drawback of the single-phase cold plate is that the liquid inside it is water or water glycol, meaning that you bring water into the server. So in case of leakage, you put in danger a lot of money. When you're talking about AI server, it's millions of dollars that you put in danger. So ZutaCore has leveraged the best of both worlds. We are cold plate, so no need for a major infrastructure differences or changes. But the liquid inside is the electric liquid, meaning in case of leakage, no harm will be done to the server. So how does it work? It's like boiling water in a pot. You have you have a heat source. The water are warming up inside. Bubbles are being formed when it reaches 100 degrees Celsius. Bubbles are being formed at the bottom, detach and float above, and turn into vapor, removing the heat away. Same thing with the processor. So the chip is heating up. The liquid inside the cold plate becomes hotter. When you reach the boiling point, bubbles are being formed at the bottom, detach, turns into vapor, taking the heat away from the server. Well, when you're boiling pasta, no problem, that's fine. But the problem is, when we're dealing with chips, if the bubbles are being formed at the bottom, it means that it creates a hotspot underneath each bubble. So some of the components underneath will not be cooled. And this may cause throttling. So it's not that easy to implement for chips. To solve this issue, this challenge, ZutaCore developed unique structures of fins and wicks, like a sponge-like material inserted between the fins, preventing the bubble from being formed at the bottom of the surface. You can see here, this is the inside look, you can see it. I like going. Okay, so no bubbles are being formed underneath. Everything is just between the wicks and fins and above. Let you see this. Okay, I will also give you a glance inside the... Oh. I had a movie here. Oh, excellent, better. Okay, so this is how it looks inside the cold plate. Through the blue line, to the blue tube, liquid is entering the cold plate. It's up. The dye at the bottom is eating up the liquid. It boils, turns into vapor, and vapor is coming out through this red line. Also, each cold plate, actually, it has its own individual mechanism, providing the exact amount of liquid required. So you see this, this valve. If you noticed, when the level of the liquid lowered because of the vapor, because of the boiling process, more liquid enter. So each and every component receives exactly what it needs. And the pool of liquid is there all the time, preventing it from warming up. So cooling is being done instantly. The minute it starts to boil, more liquid will enter, keeping it cold at all time. Now I'm going to tell you about the system, how it's built. So you have HRU, heat rejection or heat recovery unit, where the liquid is the liquid is coming out of it, distributed to the server, and the vapor is being condensed back to liquid. This is located at the bottom of the rack. You have the manifold on the side. So I'm left-handed, so it's a bit okay. So the liquid is coming up through the manifold into the server, and into the cold plate inside the server. When it boils and turns into vapor, the vapor will go out through the red line into the manifold, down to the heat rejection unit, and will be condensed back to liquid, and so forth. This is how it works. This is how it actually looks. So we have different cold plate for each processor. It has to be specially developed. It's not one size fits all. It's to fit exactly to the kind of processor. These are a bit, this is an old one, but this is H100 and this is AMD. So, and of course we're working on B300. Maybe you know that. So these are the cold plates. And this is how they are placed inside the server. Just an example. Of course, for AI server, it's going to be much more complicated and with many more tubes inside. And heat rejection, we have two kinds. One where the vapor is condensed back to liquid by air in case the data center doesn't have water facility. And when it does, so we have these units condensing the vapor back to liquid by the facility water. And this is the manifold distributing and collecting the vapor. So using two-phase to sum things up, using two-phase direct-to-chip liquid cooling has many advantages on all levels, data center level, the system or rack level, and also on the chip level. When you talk about data center, you can have reduced CapEx, since you will need less equipment for the cooling. OpEx, it retains very low maintainability, no issues. For instance, with water, you have to make sure it's balanced, you have to maintain it a lot, and to make sure no biological growth and the chemical balance is fine. When using the electric liquid, there is no need for that. Also, maintainability is very easy, as opposed to emergent, where you have to take the whole server out with a crane. Here it's very simple, you just pull out one server, do whatever you need, and put it back. The energy is more efficient than reuse, and of course you can use heat reuse. On the rack level, you can densify the rack. Since we can support higher temperature of processor, you can densify the rack, put much more load on each rack. Like I said, no risk to the IT in case of leakage. And of course, it's more efficient energy-wise. And on the chip level, we can support much higher CPUs, GPUs, much higher power. Like I said, instant cooling, also uniform cooling. Everything, like I said, because everything is, now the chiplets are more complex, but in our case, every part receives exactly what it is needed. We are not limited by the hottest component. So you can see on the left, data center cooled by a regular air cooling system, and on the right, the same one cooled by ZutaCore. And you can see that the gains you receive by space saving, money, because you see you can use much less equipment, and all the environmental benefit. You can also, like we said, you can use, you can incorporate heat reuse or even reclaiming energy. Yeah, that's it.
The first presenter will be Başak Bayraktar from VSP, and she's going to speak about CFD simulations, why it is important, what it is actually, how does it fit into the toolset of HEATWISE. And then we will have still in this session a roundtable before lunch, which will be led by Ariel. So Başak, the presentation is on the screen, and then please just...
Okay, hello everyone. So I'm going to tell about energy efficiency enhancement into European data centers through CFD modeling, and as Attila said, why it is important, what are the possible outcomes, and how it can be a product within a larger scale. We all know that data centers are among the fastest growing energy consumers worldwide, with especially AI and ChatGPT tools introduced. It leads some kind of cooling inefficiency, which is leading wasted energy, higher operational costs, and increased carbon footprint. So there is another concern that how we can keep our environment in a good conditions, in a sustainable condition. So therefore, there is a growing need for validated KPI-driven strategies to optimize cooling performance in line with the sustainability and regulatory goals, such as European Union Energy Efficiency Directive and ASHRAE. So we have two data centers as a pilot within the CFD efforts that we made. So the first one is Poznan Supercomputing and Networking Center. The layout comprises of the open aisle data center, consists of 2 rack cabinets. Is cooled by ceiling-mounted 2 cracks, especially designed for the rack cooling, and ventilation unit. The Aalborg data center in Aalborg University is equipped with 6 racks cabinets, it's a bit larger, and 2 fan coils units utilizing the air-cooled system. And both PSNC and Aalborg data centers serve as a pilot data centers, which is driven by the within the HEATWISE project, providing I'm sorry, I'm a little bit nervous. Funded Both the PSNC and Aalborg data centers serve as a pilot data centers in the European Union funded HEATWISE project, providing benchmarking cases for assessing and improving energy efficiency of server rooms at the tertiary buildings. So, as you can see, we start our CFD process by identifying the layout, because identifying the layout is the first step that we are going to take to implement our to implement the layout to our CFD model. So, firstly, for simplicity, we put the layout into our spreadsheet separately. The first one is actually layout of the PSNC. The second one is AIW, Aalborg University's data center. So depending on the server, depending on the data center's layout, actually, you can construct your model whether server level or rack level. So if you have empty servers in the one rack, maybe it is more sensible that you will going to use server level modeling. But if you have many servers in the in your rack, so you are going to use rack level modeling to identify the cooling capacities and other model inputs for better accuracy, actually. After a bunch of layout efforts, we identified that the PSNC, the total IT load of the PSNC is actually 4.08 kilowatts, and the Aalborg University's total IT load is 2.25 kilowatts. After identifying the layout and the input power consumption and the inlet temperatures, how they are provided to us by experimental and empirical efforts that was made within the data centers. So key operational parameters were measured in both the PSNC and Aalborg data centers by anemometers. I think anemometers measure the airflow velocity. So when you have the airflow velocity, actually you can calculate the Reynolds numbers, and Reynolds numbers give you the flow region that you're going to deal with. So server power consumption is another key point, because you are going to model your you are going to model heat source in your safety system. So this is another important input. Server inlet and outlet air temperatures and the airflow passing through the servers. So what is our model layout look like? Our workflow chart is in here. So firstly, we decide the server or the rack level modeling that we are going to use. It's based on the data centers layouts, as I said before. So after that, we have to construct our computational mesh, because of the it is actually how you can it is the web that you are going to predict your solutions step by step. So you translate the physical domain into the numerical domain in order to get the partial differential equations result. So it's really the key point of constructing the accurate mesh as much as possible. Within our models, actually we used block mesh and SnappyHacks mesh. Okay, after computational mesh phase is finished, we identify our momentum sources, heat sources, buoyancy flow, because we have convective heat transfer. Therefore, we have porosity as well, and Forsey-Darheimer model we constructed for the porosity modeling. And we built the thermophysical properties such as dynamic viscosity and specific heat capacity and thermal conductivity and such key parameters. So everything we need, we obtain from the experimental setup that the pilot data centers conducted, and then we implement to our system, computational system, numerical system actually. Then we implement the governing equations. I'm going to show them after this slide. So how we can validate them with the empirical data. So we have empirical data such as inlet and outlet temperatures. We have power consumption, but the power consumption is not the output. So the data that we are going to compare with is the inlet and outlet temperatures. Then we go into the phase, KPI phase, because we have to address these results with the energy efficiency metrics that is introduced by the international authorities that we have to rely on strictly. If the outcome of the metrics are okay and there is no much improvement areas in that, so we are done, but mostly this is not the case. So we have to, sometimes do retrofitting. We have to sometimes do retrofitting. Maybe this can be only the geometrical frame, the geometrical maybe it sometimes can be physical, maybe it sometimes can be operational by interfering the maybe pressure difference and pressure drop. But it's up to pilot data centers demands actually. So we only sometimes have to interfere the geometrical change. That's actually what we do within the scope of this work. So this strategy is record positioning, containment implementation, and guided airflow control, etc. to trap the cold air. I'm going to show them after this slide. So if it's okay, not improvable anymore, so if we achieved the target that we had before, so we end up with the retrofitted design. That's basically the workflow of our CFD model. So, as I said before, we first implement continuity, momentum, and energy equations if we have three-dimensional airflow. Then we have turbulent flow. Actually, the turbulent flow is the trouble side of the because which turbulence closure model that we are going to use is actually really a big point. So we constructed shear stress transport SSE turbulence closure model because there are traditional models, the most known models that are key omega, key epsilon, and SSD models, and Darcy Spallet Almaraz. But in the boundary layer, there is actually no slip boundary condition above the throughout the boundary. So we couldn't use K epsilon. So we used K omega within the boundary layer, and outside the boundary layer, we used the K omega, K epsilon, K omega. Yes. So we united them. And we add the SSD turbulence closure model because we have convective heat transfer, we have buoyancy, and we have dissipative mechanism because we have heat transfer. So we have to add the SSD turbulence closure model. So we end up with the data center DSC. So this is the open source tool that we have created, and it is scalable. It is open source, so you can. It is not open source. Yeah, it is. It has trademark. Okay, but we have used open source tool. So the data center DSC is a customized open form solver developed by DSTech. It has single framework, so once you execute it, you don't have to implement any other type of scripts or anything else. We conduct thermal simulations. So even if we have specific geometry, rec layout, and operational conditions for the specific data centers, it can be implemented to the other data centers or tertiary buildings because the basic logic is the same actually. You just need to change some parametrical things, not a very big deal about the algorithm changes. So it's really usable, I think. It's too much detail, I said before. So how we validate our CFD models results? Let's check the results. So the first one is actually absolute the temperature difference between the experimental data and numerical data in terms of the inlet temperature to the servers. As you can see, the only biggest maybe temperature difference is at the RNAP server, because RNAP server located 90 degrees in clockwise. Therefore, there are the airflow coming through the other servers which aligned linearly. So it leads thermal mixing a little bit. So it leads discrepancies around the server. So that means that we have a little bit wider temperature difference in the RNAP server. So in the PSNC data center, temperature measurements were recorded directly at the server level because we did server level modeling. Yeah. In contrast, in the Aalborg data center, measurements were collected at designated points on each rack. So they collected the temperatures rack by rack. So we did rack level modeling. Average absolute temperature differences between numerical and experimental data were calculated as 1.3 Celsius and 1.6 Celsius at PSNC and Aalborg data centers, respectively. Oh, okay. And discrepancy around the RNAP server, as I stated before, because of the location of the server horizontally. So KPIs are really important to address the performance of the cooling system and the performance of the cooling system. So we have several kind of indexes. The first one is the rack cooling index. It measures cooling efficiency of a data center by comparing several inlet temperatures with maximum and minimum recommended values regarding to ASHRAE standards. So the maximum recommended temperature should be 27 Celsius. The minimum recommended should be 18. The maximum allowable and minimum allowable should be 32 and 15 accordingly. Rack cooling index calculation is in here. Actually, the denominator is the denominator is calculated by inlet subtracting the maximum recommended temperature to the inlet temperature. So this means that how far you are from the recommended temperature, server inlet temperature, and this is the metric of this one. The return heat index compares total IT heat dissipation to the heat removed by the cooling system. Higher RHI values indicate better cooling efficiency and reliability. The return temperature index compares return and supply air temperatures of the cooling system. The return temperature index can be calculated with this formula. So actually, the closer value to the 1 means that you have higher efficiency system, which means that the difference between the return temperature and supply temperature is lower, is very, very lower, maybe almost 0, but this is not very possible in the real life because there are some heat dissipation methods and friction and some dissipation mechanisms. So closer as much as to the 1 is our desired value, target value. And as a DS Tech, we proposed one more index, which is the recirculation index, to assess the impact of the recirculation on the rack. Hot air dissipates from the server and then maybe come back. And this means that we have to address how it's measurable. Yeah, I mean, we measure this with the recirculation index. And this is the target and allowable range of KPIs table. And this is the original layout of the PSNC and Aalborg University's KPIs. And we have improved them together in communication with by introducing some retrofit ideas. And we especially increase RHI, RI, and the RTI is a little bit higher than we desired. And RHI, RTI, and RI improve when hot and cold airflow remain separated and hot exhaust air is directed toward cooling units. RCI may decrease even under efficient airflow if cooling capacity is insufficient or if inlet air is already below recommended ASHRAE thresholds. In such cases, operational parameters, supply flow rate, and supply temperature must be optimized to maintain adequate RCI. For retrofitting of the PSNC data center, there was a cooling ventilation return very close to the cooling supply system, air cooling systems. That means that actually the cool air that you give is almost sucked by the ventilation return. So it was a recirculation of the cold air and bypassing of the cold air, not bypassing of the cold air, but we added a separator. We introduced the idea that adding separator, and then trap the cold air to the desired areas rather than the undesired areas. So design change 1, removed ceiling mounted ventilation units and introduced airflow management separators to enforce hot and cold aisle containment and minimize thermal mixing. Design change 2, sealed the front and rear surfaces of inactive servers to prevent the heat transfer, undesired heat transfer, and to prevent the air leakage, maintain efficient airflow and reduce cooling losses. And retrofitting strategy, we only did geometrical change. We did not interfere any supply temperature, mass flow rate, or this kind of coolant properties. It is up to pilot data centers, demand and HEATWISE regulatories, I guess. As a result, we observed 50% of improvement in return heat index. We have 35% enhancement in recirculation index. What are their benefits? It mitigates hotspot formation. It prevents cold air leakage into non-essential areas. It achieves more uniform thermal conditions. It reduces energy consumption and improves system performance, and is cost efficiency as well. What we did for Aalborg data center, we did also add separator because server racks aligned with the fan coil outlets to reduce the airflow resistance and ensure efficient cold air delivery. And we introduced round racks to enforce hot aisle, cold aisle containment, preventing thermal mixing as well, and improving temperature uniformity to trap the cold air to the desired areas, actually, again. The additional separators are added. So narrowed flow pathways minimize cold air bypass and directed cooling precisely to critical heat generating areas. And we did the same thing. A sealing unused server bays prevented leakage of cold air into inactive zones, ensuring airflow targeted active servers only. So it is really, I think, useful. This is the layout you can see. How much time I have? Okay, so as a result, we have observed that the 75% improvement in RTI and 18% of enhancement in RHI. What are the benefits? We have improved cooling efficiency in airflow and airflow containment. We have reduced operational load on fan coil units, and it means that you will have lower electricity bills. Minimize cooling losses and energy consumption as well, and enhance temperature uniformity and reduce risk of localized hotspots. What is the value of this project? So it provides a replicable framework for KPI-driven cooling optimization, and it is scalable. You can even use this framework to the data center, or maybe even to your home, actually. Demonstrates measurable concrete results, lower energy bills, improved reliability and extended equipment lifetime, supports sustainability, branding and compliance with European Union and ESHRE directives. The validated CFD and KPI methodology can be applied to any data center, and opens the door for collaboration with operators, vendors, and technology providers. With our solution, data centers don't just run, they run smarter, greener, and most cost-effectively. So we have only one word, yeah, we have to keep it green.
Then we come to the next presenter, to Mustafa. So thank you very much, Başak, again. So let's see, we have already a data center working, we did the retrofitting, and then there are still KPIs to measure, and this is the next tool in our tool set of HEATWISE, a self-assessment platform or self-assessment tool. Please, Mustafa, go ahead with your presentation.
Thank you, Attila. Hi, everyone. I am Mustafa Kuzay. I work as a lead safety engineer at DSTech. Today, I'm talking about development and implementation of self-assessment tool. Why data center efficiency matters? Data centers accounts for a rapidly growing share of global electricity use, you know. Rising pressure on energy efficiency and sustainability goals is driving data centers to adopt more structured and measurable assessment practices. Since 2024, the European Union's Energy Efficiency Directive mandates reporting and continuous performance improvement. So our main goals is following the two rule makers. One of the Energy Efficiency Directive, and another rule maker is European Data Center Association also. Energy Efficiency Directive, mandatory KPI-based reporting. Also, data centers with IT capacity exceeding 500 kilowatts must provide regular assessment reports. Today, reports are manual, fragmented, and time-consuming. Also, according to the recent European Data Center Association's report published in 2025, approximately 36% of eligible data centers participate in the first reporting period. Around 80% of submitted data were deemed accurate and reliable. Low overall participation highlights challenges in data center accessibility and energy efficiency reporting across the sector. HEATWISE offers an automated and reliable reporting tool that is both auditor and user-friendly. It's aligned with also EU sustainability objectives, delivers KPI-based reports with the Energy Efficiency Directive. Also, it's aligns with the ESHRE standards. KPIs in self-assessment tool, we have 21 KPIs for the one of the thermal KPIs, another ED KPIs. ED KPIs provides the ED KPIs based on the power also. Overview of the self-assessment tool. The self-assessment tool has been developed standalone, both standalone version and also web-based service within the scope of HEATWISE project. The self-assessment tool can either retrieve data directly from the data center data monitoring platform or also external sources. Finally, the self-assessment tool generates ED-aligned comprehensive assessment reports based on the provided data sets. Self-assessment tool provides automated data capture from the sensors or monitoring system. Also, self-assessment tool calculates real-time KPIs from the data. Also, self-assessment tool visualization is KPIs displayed via color-coded heat maps, trend graphs, instant and average values, and also assessments. We have, as I said before, we have two versions of self-assessment tool. Standalone version can be deployed independently without external dependencies. It's a little bit secure, I think, for the data centers. Also, self-assessment tool fully customized for each user. No data is exported or stored externally. Second version of the self-assessment tool is web version. Web version is easily accessible through the secure web login. And also, it requires the data center to provide real-time data. Properties of self-assessment tool are, we are developing phase for the self-assessment tool. We gathered data from HEATWISE pilots and also 5 external pilots. And finally, self-assessment tool generates a report. The self-assessment reports provides, as I said before, it provides data center information, also KPI assessment, KPI descriptions, thermal heat maps, also server layout of the data center. Market value of the self-assessment tool. Self-assessment tool provides automated and consistent report. Also, it detects hotspots and inefficiencies, and it provides compare across sites for the benchmarking. Also, promote green and efficient operations. Self-assessment tool saves time, no more manual reporting, and supports cost reduction and supports compliance and strengths brand. I want to thank to H1 system also for the development of the self-assessment tool. Self-assessment tool provides so many advantages for us. Automated or manual with smart validation, low risks, high security, consistent KPI structure and templates, auto-generated reports and dashboards, also scalable to multi-site and multi-user use. Thank you.
Let's step further, and I would like to call Csártály to the floor. Csártály Yilmaz from RISE, the Swedish Research Institute. He's coming from the data center department. So he's going to talk to us about the integration of data centers into the energy grid and the potential in digital twin. And he's going to give us, I think, an overview how we plan to do this in HEATWISE.
Yes, and I'm also hoping to answer some of the questions which is just asked, because, yeah, let me start with introducing myself, Csártály Yilmaz from RISE Research Institutes of Sweden, with my esteemed colleague. So you can just say hi, Henrik. Yeah, so after, especially during the coffee breaks, please catch us. Because what we're gonna talk about, I agree, many things are a bit controversial. But if you really want to change something in the market, I think you have to be brave. Sometimes the solution is right there. I'm not telling it's easy to be implemented, but still we try to do our best to change something in the market. Yes, probably you all heard the common stress about the data center market and how energy hungry we are and how the demand is actually growing. But in this graph, this is not the latest, the most like up-to-date graph, but I like it because it is symbolizing things like how the things can go in a good way or in a bad way, and how a distributed computing paradigm, which is highly related to what we are going to talk today, can affect it. The green line that you see here, it is the dream scenario. You know, whenever EU introduces us something, a new program, that everything has to go really in the best way, so we're going to achieve these goals. It never happens, but it is a good start, because in the worst case, we actually go with the red line, that if we can actually take an action. The blue line is the current trend, and I think it's brown, right? The brown line, it's a bit interesting. This is talking about the effect of edge computing, or it is the effect of a distributed computing paradigm. Why it's important? Okay, I participated multiple projects under EU, especially I will reference here the Edge Observatory project, where we try to define what is edge, and we built a taxonomy for the edge computing. Between us, I think EU and on the global level, there is no global consensus of what is edge, what we should call edge, what is fog, because if you check from different perspectives, if you check from the industrial perspective, edge and fog, it's a bit different. And if you consider, like me and Dennis, like more thinking about the data center level, for us, edge is different. What I can tell, I think edge can be identified case to case. So a few megawatts of really big data center can be our edge node, depending on how we use it. So why it is a threat? Why I started telling that it's a threat? Because we have the demanding industries. Like I'm usually asking people when I start talking about edge, how many new devices you added in your home network in the last 2-3 years? Right? Everything started to be smarter and smarter. I mean, I'm thinking my cat feeders, my washing machine, my car, everything is now connected to the network. And most of the things that I mentioned here, they are not requiring really fast, low latency rates, because it wouldn't hurt when you just press enter in your computer, and if a web page or an application is loading a bit late. But if you are building an application which is going to detect one accident on the road, and if you are creating a live map of a fleet, and if this car's accident has to be communicated to other cars for them to take the necessary action, then latency is important. Then it is not only about a globally distributed compute paradigm is important, it is also important what kind of communication that you use, and it is also important like the computational capacity of these edge nodes that you are using, because we have these latencies coming from the network side and from the compute side. So there are many initiatives in the EU, I would say, which is focusing on how we optimize this. And I usually use Legos to define this. Basically, we have the smallest building blocks, like the nodes, I would say. And depending on your need and the creativity, you actually find different solutions, and you distribute them in the globe to make sure that your applications are receiving the right network and latency statistics that you have. But as mentioned, this distribution is not going to be like, oh, okay, hyperscalers and really small edge nodes. It is like a totally heterogeneous environment. At least this is what my observations are. So why it is important? Because yes, we have cloud. I say cloud because I believe personally the edge nodes that we are talking now, which is backing up the European digital decade, they are multi-access edge nodes. They are cloud-like structures, 11 cloud-native applications, and so on. And they are everywhere in Europe. They are more dense. I'm just giving an example here. They are more dense. And once we actually distribute them all around the continent or globe, we have some issues. First, we need energy. We need network. And it is not that easy. Like when you build an 80 megawatts of hyperscalers like Meta did in Luleå, where I live, up in Sweden. So everything is pre-designed, right? You talk to grid, you talk to municipality, you have some backup plans. But what happens if these units are smaller, like 100 kilowatt, 1 megawatt, then can we still like adapt ourselves to have the best integration into grid? Can we still spend the right budget and time to build the right systems for the optimum efficiency? And maybe the most important thing is, can we actually justify the efficiency metrics of a data center in Sweden, which is relying fully on renewable energy sources? And can we compare them with a data center in Turkey, for example, or in Germany? So a lot of questions in mind that we are trying to build some solutions to answer most of them. But today we are going to talk about mostly the byproduct of this process, which is heat. And heat is a byproduct which can be used and reutilized for different purposes, which we will discuss. And also it affects significantly the performance and the lifespan of the IT. So we have to make sure that this byproduct is controlled in the right way and reutilized. So we discussed about grids, and talking about these grids, we have multiple aspects that we can focus and we can optimize. Yes, let's start with waste heat, because we are in HEATWISE projects meeting. Basically, heating and cooling is one of the fundamental parts of the data center management. So in a life that we actually deploy data centers and interact them with the energy grids, one of the aspects is electricity grid, and the second aspect is the heat grids. So this is something when we are optimizing, when we are integrating data center into the energy grids, this is the first aspect we consider. The other aspect is the renewables in the grid. The other one is energy pricing and the carbon density. Maybe this is not valid for all the grids in Europe, but there are some really flexible smart grids that we are keen on developing some flexible solutions for these grids. And most importantly, IT load. Yeah, when I say IT load here, most of the experts from data center market, yeah, I understand. We don't want anyone else to come and touch our IT load, but maybe there are some safe approaches that we can actually create a win-win between the energy grids and the data centers. Just admitting you, I'm also telling it to my colleagues all the time, usually I work with data center people. We really understand each other, and it's really easy to communicate. This is my first project that I'm working with the experts that you met before from the building side. So these are all great challenges, actually, which will be taking actually our technologies better suited for the markets and energy grids. Yes, not easy as discussed, but it's happening, and I hope Europe will be leading this market. So talking about the byproduct, heat, our main idea is actually turning data centers into the boilers of the buildings and districts. How we can do that? I think what the building side, Aalborg University presented, it's really promising, because understanding the building size demand can actually help us more flexible data center operations and more efficient data center operations. But what the technology we adapted in this project is important. We are going for direct-to-chip liquid cooling because the heat fluxes and IT intensities per rack are going skyrocketing. The new applications that we actually provide infrastructure for, they are becoming more and more challenging. So it is the best way is to go for the best cooling solution in the market, which in this case, direct-to-chip liquid cooling, especially a two-phase direct-to-chip liquid cooling, is giving us a great advantage. What is this advantage? In most of the cases, we want to provide high level, high return temperatures to the building or district, not to risk it. And to be able to make it, we need to control the cooling on the chip level. And especially my team, of course, collaborating with other work packages, is focusing on how to optimize this process to make sure that we provide the highest temperature returns while not sacrificing from the IT efficiency. So as discussed, two-phase pool boiling direct-to-chip cooling is the technology that we are using in this project. And of course, you listened a lot of presentations today. This is a research and innovation project, and we are now building the foundations of understanding this technology, its limitations and its advantages, and how to turn them into real products in the future. This is the gap we are trying to fill with this project. Then, once we understand the limitations and advantages, we want to build a holistic data center management system on the top. This is a really difficult path, I have to admit, but it aims at collecting the right data from the data centers and making sure that both hardware and software components are decoupled and controlled in the right way for the maximum efficiency. Yes, also in the previous presentations, we discussed about one factor. I think Europe is leading the sustainability part of the data center operations. And I would say, like, I'm in multiple communities, and especially like Open Compute Project, etc. I'm really happy when I see more and more European companies representing the cooling side, basically leading the cooling innovation in the global scale. This is amazing. And directives, you know, one of the biggest concerns in the market, Europe is driven by regulations, not the innovations. It is sometimes slowing us down and giving us challenging times. But sometimes I want to believe that whatever won't kill you makes you stronger. And we have to adapt to these regulations way earlier than our competitors in US and other countries, right? So I want to see it as an advantage. And when we were writing this proposal, actually the Energy Efficiency Directive and their KPIs, they weren't there. At the end of the day, I'm happy. It is a great proof showing that when we started working on this proposal, we are actually going to the right direction, because the major KPIs in the Energy Efficiency Directive, it's already our targeted in our targeted KPIs list when we developed this project. So energy reuse factor here is the key KPI I would like to say that we are focusing in the HEATWISE project. But, okay, I will start some conspiracies here. I'm not a big fan of all the data center KPIs. I don't think there is one KPI, like the theory of everything, which solves every efficiency issues in the data centers. I'm usually giving this example, PUE. I'm not a big fan of it. I use it, but not a big fan of it. Consider, in the wrong hands, PUE can be really dangerous. Let me explain why. PUE compares data centers' energy consumption with the IT systems' energy consumption. Some argue that, yes, it is apples and pears. If you compare different data centers, it is not good, but you can actually see the same data centers' improvements over the time. But what if the data center manager or operator has changed and they changed the cooling settings? And what happens? Giving you an example, case 1, case 2. The first one is cooling right. The second one is cooling insufficiently because somebody somehow by force increased the inlet temperatures. This is an air-cooled system, just for you to understand. The difference is here IT system is consuming less for the same work. And the increased temperature case, IT system is suffocating. Not enough cooling is provided. In the end, the data center is consuming more energy, even though the cooling is consuming more in the case 1. So what happens? Your PUE is actually better in a scenario where your data center actually consumes more, and you actually significantly reduced your components' lifespan, because most of them are not cooled well. And it happens actually the same for the heterogeneous systems. Like when you set up, I mean, I really appreciate Esri, but when you actually control the cooling temperature or relative humidity in a room, are you sure that your whole all systems, all nodes in this cluster are cooled well. No, we have an assumption. It is good. These standards are there for years because they work. But again, more heterogeneous systems, more intensive loads, I better not to risk it. That's why we started working in these projects. What is the solution? Actually, coming to the answer of the question, what happened to John? Okay, interesting. This picture looked way better. This is John Summers, our scientific lead in ICE Data Center. What we do, we want to make a purpose, or make the useful data, sensor data from servers especially, and the ecosystem components. Usually people track the ecosystem components, cooling, etc. But this data is not well used. Yeah, you go to your ID rack, you go to your like data center infrastructure management systems, you get a glimpse of this data, and you trust this most of the third-party solutions because they are trusted in the market. But once an EU project develops a solution for this, I understand. It is raising a lot of questions. That's why we try to make a lot of our solutions open source if we really need to work with market, for our end users to see the code, understand what they are doing, and deploy it on the site. And we use like MQTT messengers, etc., where you can control which data we should get. This is only one of the safety things that we are discussing. But please keep in mind, these are all research projects. We need more time to actually evolve them. Anyways, this whole list, sorry, it's not looking so good, but this is all the useful data we collect to maintain the server, like the board management system of your server collecting this data and adjusting your fans, maybe thermal throttle in your server in case you are not cooling it enough, then it's garbage. We are not using this data at all. And our idea actually starting with the Wooden Type DC1 project, HEATWISE project, now, EcoCube project, and now this project, step by step, increase the usage of this data because now we can do it. Now, current technologies are more making this data useful for us. I will just try to explain why it is important. Giving you an example, inlet and outlet temperatures of the servers are taken from here, on the board. CPU temperatures, wattage, memory temperatures, wattages, everything. I mean, really, really important information which can be useful for system level optimization. It is lying in here. So what can be done with this data? Yeah, it is really difficult to make a use of this data. And once, for example, you get all the CPU frequencies and visualize it, it doesn't make any sense. Then you actually process this data, create clusters, and compare different CPUs frequency. Then, okay, there are some differences. Then you start thinking, what is the reason for that? And then you spend more time on this data. Just giving you an example, like when we say big data, focused data center management, I try to help you to visualize what it means. For example, this is an OCP Leopard version 2.1, I think, server. And first CPU is getting better cooling because it is first in line. And the second CPU is basically getting a bit more warmer inlets. It can't be simplified by this. There are many factors actually explaining the frequency response of the CPU, yes, but if you have all the data and all the variables, and if you can control it in a way, maybe not it's easy for a human, but computers can help us to process this data and make some meaningful outcomes from this data. As you can see, what is the reason that always the second CPU work with lower frequencies? I don't have the answer yet. We are working on it. There are multiple variables. Without conducting a lot of tests, we can be sure. But these are the questions that we should be asking to ourselves. And in a data center, maybe the first CPU and second CPU scenario is happening in hot air circulation zones. And actually, Diestek mentioned about them. Like, we are not really knowing what is happening in our data center. Am I going so slow or? Okay, good. Good, great. Okay, so let's discuss more about waste heat reutilization, and I want to study a bit more another KPI, energy reuse factor, and let's talk about cases again. The first case, I have a data center, consuming 10x, and it has this new cooling system. And this cooling system, from the heat rejection unit, it can provide 65 degrees, which is totally good for my building temperature regime and temperature requirements. So what I do, I use, except the losses, I may be recaptured in a good day, 9x of the waste heat, the byproduct we generated, and energy reuse factor of 0.9 I achieved. Amazing. But what happens if I have a data center which consumes the same, but on the top of it, because it can only give me back 50 degrees, but 50 degrees is not acceptable for my building. Maybe because of these bacteria issues when I want to supply it in the system, I don't know. But then I had to add one heat pump, and heat pump consumes 2x. In total, it increased my data center's consumption. The cooling system is working fine. The IT is working fine, but building has some restrictions with the heat demand. Then what happens? Look, our ERF dropped to 0.75. So these are the things that we are working on right now, trying to orchestrate the full system and make sure that the return of the temperatures are maximized, or not maximized, but we control the system to answer the demand of the building when it comes to total accumulated of energy and the return temperatures from the data center to the building. So then we actually make sure that we are going to do more efficient location. Of course, there are also other things like what happens if the heat pump is outside of the building. So how we can justify, how we can recalculate everything. Yes, many people now we are discussing about it, but this is more realistic. If the temperatures are not good enough, then we have to increase them, right? Okay, talking about value of data, we discussed about the server level data. I will give more examples about it, but also the building side. Telling you, first time working with the building, it's really exciting. This graph is representing our buildings' heat demand through the year. And I have to say, during winter time, it is around -20, -30 degrees outside, and the heat demand is significantly increased. It's a warehouse where multiple companies are using it, and we use it to run our data centers. And during the summertime, as you can see, the demand is minimized. So basically, what I can do with this data to make sure that I can improve my data center operations. This was one of the questions that we are asking to ourselves. And the team being led by Henrik, they conducted studies to turn this data, get some external API data like the forecast of the external temperatures, etc., to make us have some predictions about the building's heat demand in this close future. So, which means that, yes, like this, you can see in the blue line here. So, which means that if I know how the temperatures are going to change, I would actually can guess how much the heat the building will need. And if I'm operating with a lower, IT capacity, maybe I can increase it. With dummy loads, or I can do mining and I can earn extra money, who knows? But these are the business cases that this research project can actually lead us. I will come to that, but if the building requires less waste heat, then in the future we can try, if it is beneficial and economically feasible, move the workload. But these are the things that we continuously work on it now, because moving the data is not the best idea all the time. So as a summary, we are trying to build a reasonable bridge between the data center and the building, where our algorithms are fed with real data and supported with a digital twin. And what we can do, this is just one example, the variables of this operation. It's a multi-variable control problem, I know, but giving you an example, we can actually understand the external temperatures effect on the data center and building, and we can then try to understand our heat customers in this project. Then we can also understand the outdoor temperatures effect on the cooling system and our energy cost, cooling side of the costs. We can track the district heating integrations to minimize our cost on the district heating. Then the whole system, step by step. This is not, of course, something we can do together, but EMPA and Albury University, these are the building sites. These are the real bosses managing all the energy grid. So this is the whole ecosystem can be controlled and improved in a better way. And we can do it, if we can put a few people in front of some screens and we try to make sure that we will step by step improve the things. No, we need digital twins. We need smart algorithms to make sure that with minimum human interaction, the whole system is automatized in a way. Okay, last slide. Maybe there will be questions, I don't know. What's going to be the future? This is out of scope of the HEATWISE project, but I want to share our vision with you. What is going to happen in the future? So you have some data, and you want to process this data, make this data useful for your business. So what you do, you train your models, foundation models, or you run your large language models to improve your operations in your business. What you can do, if you need a supercomputer HPC, you can just come here to Ariel and say, I need some resources, I need really good resources, please provide us. You can use some public cloud. You can maybe think about investing in some on-prem solutions, edge solutions, and finally maybe you want to aid this data with some IoT data to improve the operations. Then what you can do, you have to have some federation capabilities in this heterogeneous environment. And if you don't need HPC anymore, unplug it and plug it another cloud. So this is our vision, what RISE is trying to do for the future. But HEATWISE has a significant importance for us, because it is not only about managing this heterogeneous environment, but also making it sustainable. Then we actually now listen the demand from the buildings, and we actually take it as a consideration in our management considerations. Like altogether, we believe that this is how the future is going to look like, and hopefully HEATWISE is going to be a great contribution for this. Okay, I'm done. Yeah.
Csártály, thank you for this impressive presentation. Okay, so let's move on to the next etap and to the roundtable. So this will be led by Ariel, and I would like to call here to the stage our roundtable panelists, pan Piotr Kowalski, pan Radosław Górzeński, pan Radosław Januszewski, and Andrzej Kuliński. And before I would give the microphone and the stage for Ariel and our esteemed panelists, I would like to call your attention that there will be a QR code picture here in the screen, which is going to be a quick survey to you. Please scan it and give your opinion about our event. Thank you, Ariel.
Yeah, thank you. Okay, so first maybe some context of this panel. So you could see a lot of presentation from the actually research and development project. Yeah, so from containing some tangible results like ZutaCore, like hardware, but also some methods, proof of concept, and so on, and with a quite broad scope. Now we would like to just focus on the waste heat potential, first of all, and then also we just invited experts from real environments where they have very concrete requirements, and that's why we would like to discuss them. What is the real possibility and the potential? Yeah, so that's why I would like to introduce first of all our panelists more. So Piotr Kowalski is managing director of Polish Data Center Association with big experience in data center market. Radosław Górzeński, he's an environmental engineering expert from Poznań University of Technology. And if you look around all these buildings around, yeah, I think you're involved in most of them, yeah, and even now you're involved in the nearby building. Radosław Januszewski is a head of new HPC architectures department at PSNC, so he and his team is managing, installing, managing, operating the HPC clusters at PSNC. And Andrzej Kuliński, Energy Efficiency and Climate Director from Veolia, so the large international company which in Poznań operates the district heating network, the large network for the whole city. So that you can see that we have quite complementary knowledge and expertise from our experts. Okay, so let's start. I would propose to start from first from like a question discussion about technical feasibility of such solutions. Yeah, so if first of all to reuse the waste heat, we need to produce it somehow. So the first question to Radosław Januszewski. So how would you? So what heat loads and temperatures we can expect from HPC system, especially if you compare it to the traditional typical data centers, and taking into account also the fast changes now with this AI boom and you know, requirements.
Okay, that's interesting point of view when you look at like a multi-million machine as a very expensive heater. Yeah, but in a way it is very expensive heater. So answering your question, if you look for like 10 years, which is not very long time, at least in terms of like the hard infrastructure like data centers, because they tend to be designed to operate for more like 10 years, it's like more like 25 or something. We see that the energy density increased from around like, I don't know, 10, 20 kilowatts per rack. Right now, the machine that we are currently using is about 50 kilowatts per rack, and the next one, which is AI HPC hybrid, will be difficult to find a machine that is less than 100 kilowatts per rack. So it's a lot of joules, but unfortunately, at least from, I guess, your perspective, the temperature of the coolant is not increasing, and to be honest, it is even decreasing. The first DLC machine that we used, the CPUs maybe the TK's temperature was around 100 degrees, so we could use like 60-70 degrees coolant, and the machine was still fine. The current generation, because of different reasons, it's around, I don't know, the inlet temperature, it's around 30 degrees. If somebody is very brave, it can expect like 40 degrees. So the outlet, so the something that is interesting from the heat reuse perspective, is around 40 up to 50 degrees. And I don't think we will get higher, because the manufacturing process of the chips is not allowing to go like the temperatures, the TK's temperatures is decreasing with each generation, which is a challenge, well, not for us, but for the hardware vendors, because they have to cool even more joules or remove more joules using colder water. And at the same time, everybody wants to get rid of this heat as cheap as possible, so not to use chillers. So we would like the coolant to be warm, but not too warm. So directly answering your question, I guess we can expect like something between 40 to 50 degrees outlet temperature. And realistically, because the increasing the temperature is not comfortable for the machine, it would like to run as low as possible. So realistically, it's like 35 up to 45 degrees.
Okay, so thank you for the question. It's interesting what you said, because we have, the ZutaCore company here, that and in HEATWISE there are some goals to try to go even like a 60 and so on. So it's interesting that what you are saying from, maybe we come back to this discussion. Maybe first I ask questions and then we'll also ask audience about comments, yeah, because I think it's very interesting what you're saying, and the interesting point for discussion. But when maybe I will go because okay, that's from the data center side. Now, what about the buildings? Yeah, so that's why my question to Radek Górzeński. So how do you see from the perspective of buildings, what technologies are required or the best suitable to try to reduce this heat, and what are the requirements in terms of temperature? Yeah, maybe.
Yeah, first, we have to think about the buildings like, let's imagine that we have an old car and a lot of friction inside. Yeah, so when we ask, for example, what kind of heat engine to buy to this car, first we should think about retrofitting this car to decrease the friction, and then to choose the heat pump, or the engine for the car. So the engine would be 2 times smaller than before. So the same is when we talk about the buildings. The first issue, before we talk about the chillers, the heat pumps and so on, we have to think what we can do with the buildings to decrease the heat demand, or maybe not just decrease the heat demand, but the temperatures itself, and how to prepare the buildings to, for example, to changes in heat supply, values. So first issue is retrofitting. Yeah, I mean that we need buildings to be insulated, windows to be changed, maybe ventilation system, and the second is the heating system. So first issue is the area of the radiators. Sometimes it should be increased to decrease the supply temperatures of the building, supply temperatures in the building. Parallelly, if it is possible, we should use a system like floor heating or thermally activated building slabs. And I can show just an example. We have neighboring Poznań University of Technology campus. So we have buildings with 90, 80 Celsius degrees temperatures, supply temperatures of water system. But parallelly, there is a building which was erected 3 years ago, where the supply temperature is 32 Celsius degree. So when we talk about 30 or 40, it could be, it could be just heated without any heat pump. So that's the main idea, how we should think about it from a point of view of buildings.
So in short, you do not exclude then this kind of source of heat, but it's just required to prepare the buildings from your perspective, at least. Okay. Okay. So we have this perspectives from data center and the building. So maybe Piotr, could you then summarize? So what do you, which technical barriers you can see in really making this efficient heat reuse? Then what technical barriers in data centers? How from your point of view, what are the main ones to make this efficient heat reuse?
Sure, thank you. So I'll address the barrier in just a second, but first I would like to address the industries, the data center industries being ashamed of having waste heat of only 50 or 40 degrees. That's an asset. That's something that can be reused. I think the mistake, the shortcut that we're making is that we're thinking of, for example, district heating systems as something that operates at 100 degrees. We only have 40 or 50 degrees, so there's no way of matching it. But having a consistent load, having a consistent source of waste heat at 40 or 50 degrees, or even 30 degrees, that is an asset that can be utilized. There's just different applications. As Radek said, also, maybe we can directly reuse it. Czarek, I also liked your idea of removing the boiler from the building and at some point replacing it with a high-density rack. But at a scale, having few megawatts of heat at 40 degrees, that is something that can be reused. And I think, Andrzej, you will address that as well. So we should not be ashamed of that. I've been involved in many conversations where the industry is saying, yeah, but we have a low-grade heat. That's not a low-grade heat. That's an asset that can be reused. On the technical side of things, I do believe that to make these deployments at scale, we will have to have a heat pump in between. So that's the first step. That there's probably no way, at least in a shortcoming foreseen future, to directly reuse the data center waste heat, unless you can couple it like with a campus like we're in here. That's a great application, right? If you have buildings that can work with 30 degrees, if you can provide 30 or 40 degrees directly, that's a great use case for let's say, a microgrid application. But if we're looking at scale, then we will have to include an additional component that is raising the grade of heat from the level that we are able to provide to the level that the district heating network is able to operate with. That's a CapEx, right? So it's less of a technical issue, but that's a CapEx. And even a bigger challenge, that's something that we've seen, that it requires a lot of footprint. So in order to make it happen, one has to plan in advance. So it's not something that we can completely independently build a data center and then somehow connect it to a district heating network. This kind of solution must be planned in advance. And that's something that I see as one of the biggest obstacles because it requires planning up front. And that's something that we're often not very good at.
That's true. Okay, thank you. Okay, so the last question to the district heating operator, to Andrzej. So then what actually are the volumes and temperatures which are, let's say, acceptable for district heating operator to make the data center waste heat practically reusable at scale?
Okay, first of all, thank you for invitation for today's roundtable panel and possibility to share our point of view of this topic. So if we look at the district heating networks, they operate during the summer period at the level of temperatures between 65, now in Poznań, till 70 centigrades, and up to 120 centigrades during the winter period. When we look at the heat coming from the data centers, depends on technology, we talk about it, but it's between 25-30 degrees at the least, at the minimum, and at DLC technology, direct liquid cooling rises the 40-50 centigrades, which means that this temperature, this heat have to be upgraded with the high efficiency heat pumps to be implemented to be supplied to the district heating network with COP around 3, at least maybe 3.5 or even higher. But the advantage of it is that the heat from data center is stable, is predictable, what our network require, what our network likes. Of course, we've got some fluctuation during the day, during the year, but the main advantage of this heat is that this is still stable and predictable through the entire year. What more? Regarding the maybe the volumes, because Piotr said that we've got the capex. If you consider the huge investment, depends of course of the capacity of the data center and capacity of the recovered heat to be recovered, capacity of the installation. Moreover, we've got the issue with find a place with our production profile for that heat. It will be the most challenging thing, I think, with the discussion and negotiation about the business model. But on the other hand, we've got the good example of heat recovery from industry, from Volkswagen plant here in Poznań, also in Glassworks, also in Poznań. These installations are about 2 to 4 megawatts and were connected to our grid, our district heating network. So I think that for the projects like we have with Beyond, because Piotr is also today is representing PLDCA, but is also cooperating with us on the project, which we consider at the first stage 30 megawatts of heat recovery. So for that project, I think that we have a slightly different issues to be solved. than for the smaller one, because I think they are easier to be implemented, because if the output is less than 5 megawatts of thermal power, they don't need any license based on the energy law. So for small scale plants are easier to be connected and can be operated by the building operator, but for the installations like we are considering with Beyond, probably district operator should take the responsibility for build such a plant and operate it later.
So for 30 megawatts, then you already, let's say, analyzed that it's economically viable to invest in this, or it's just.
It's still an ongoing process, so we are.
Yeah, I'm not sure how much we can share about the commercial viability, because that's still in the making. Okay, but on the technical side of things, definitely feasible. So again, the differences between the temperature, not a problem, that can be technically solved. The challenge obviously is in the details. Once you get into the nitty-gritties, the formal part of the collaboration is probably the biggest challenge, and finding the right business model for it. But again, the need is there, the opportunity is there on both ends, so it's just trying to find that model. And if we look at the projects around Europe, for example, there's plenty of examples where even large-scale data center waste heat recoveries have been used for feeding a district heating system. So I'm sure the solution is there, right? It's just having probably the right mindset at the table on both sides of or even multiple sides of the table, because that's one of the challenges as well. Very often there are more than one stakeholder involved to actually agree to do it. And more than technical, I would say that's the biggest challenge, to have everyone agree to the same goal.
So sorry for this question. I promise that we are focusing now on technical feasibility, but that was my curiosity, because when we did this analysis, for us, like direct connection to Veolia at the time was not so viable, let's say. But okay, we'll come back to this maybe.
I would like just to add one issue, because Piotr said about it. But if we watch from the point of view of buildings, and to compare what we have in heat pumps, how we could use the heat. So we have air source heat pumps, ground source heat pumps, and we could use waste heat. So if we compare the average temperatures of each of these sources, with air, it's more or less 0 Celsius degree, maybe 5 Celsius degree. The problem is that it changes a lot during a year. The second issue is we could use from ground source. It's maybe 10 Celsius degree, 5, 10, and it's more stable, but it's much more expensive. And then we talk about 30, 40 Celsius degree. And in case of heat pumps, we talk about COP, so coefficient of performance. The smaller the temperature difference between low source and the supply source. So the lower this difference, the higher the COP. So if we talk about if it's reasonable or not, we have to talk about what options we have. And we have only air and ground, and each time it's the temperature difference is much higher. So the results are worse in case of air and ground source.
Okay, by the way, because thanks for this comment, and you also mentioned this temperatures of network in summer period, in winter period, so maybe that's maybe a general question to you. So what about this summer, yeah? So what about the seasons? So how do you think, because on one hand, in the winter we need more heat to really for heating system, for instance, neighborhood, yeah, let's say if you could use it. But then in the summer we have more excess heat, but you probably need less. So what is the solution for that?
Yes, exactly. And summer is a real challenging situation. For many of reasons, mainly from our point of view as a district heating operator and at the same operator of the cogeneration heat and power plant. Because during the summer period, if we recover the heat. If we take the heat from the data center, we need to reduce our production and CHP plant. Therefore, we need to reduce our electricity production. Therefore, we need to reduce our revenue on this. Mm-hmm. So this will be I think, the main point during the discussion about the cooperation with data center, mainly for the district heating operators, which also operates the CHP, because for the operator, like for example, our district heating system in Warsaw, because Veolia is also operating this system. But over there, we don't have a CHP plants. We are just operating the network. And this is totally different approach to the business model, because we can, if we connect additional recovery heat source to our network, we have a cheaper heat which we can sell to our customers. And saying it is simple was, we don't care what will happen in the CHP plant. Yes, maybe it is not sometimes in effective way, but this is a business. Yes, so they have to find a solution how to reduce the production, how to operate during the summer period. We will just buy the cheaper heat and supply to the customers, which is an idea of the district heating operations, because Polish energy law is saying directly that we have to take care about the consumers. The heat delivered to them should be in the cheapest way. Yes, so of course during the summer period we can also consider the thermal energy storages. And they are feasible, but I think that not for such a system like Poznań district heating system, because this is large system with the capacity, or maybe starting like this, that the maximum capacity demanded or ordered by the customers, if it is calculated for the worst conditions, for minus centigrades outside temperature, it is 1,300 megawatts. But during summer period, system consumes only 80 megawatts. So this is the difference. So and if we consider the thermal storage for 30 megawatts, like this Beyond project, we should build a huge energy pit as a pool of water, which consume a lot of land and probably some environmental issues. So it is not feasible for such a huge system, because for this, at the same time, for the smaller systems, for the smaller cities, I think it is feasible to build even for the weekend period. So the weekend thermal storage. We also have a thermal storage in our CHP plant, but we are using it for the balancing the daily fluctuation. So, for example, if we have a high electricity prices, but no demand from the network, district heating network, we are producing electricity, storing heat at the thermal tank, something like this, because it is tank with capacity of 20,000 cubic meters. And then if the prices are lower, or even on the other side, below the zero, we are stopping our production and consuming heat from the tank, from the thermal storage. So it is possible, but I think for the Poznań's district heating system, it's not feasible for to be applied at the data center, because storing the heat from the summer period, 30 megawatts each days for 3 months, I don't know what will be the space needed for the land.
Impressive.
Yes, exactly.
So, and other ideas then for local, maybe usage.
One word of comment, because at least from my perspective, the problem with heat reuse from data center is more like financial and formal one rather than technical, because technically we know how to do it. Like several years ago, we had like a project with several data centers from around Europe. We did something similar, like we did a study, like a survey, what you do with your heat, with your waste heat. And the results were like completely, well, at least a little bit surprising for us, because it depends where you live. People from Sweden, they said, wow, the heat is asset, we sell it. And everybody is happy that we are selling it, and it's consumed basically all year round, well, maybe with some weeks where it's warmer than anticipated. On the other hand, people from Southern Europe, they said, come on, we want to get rid of this heat as cheap as possible. Nobody cares what's happened because it's warm anyways. Mm-hmm. So we are in between. So in the summer, we have, as you said, in the summer we are like, I don't know, like Italy. We have a problem with too much heat, even with this summer. And in the winter, we are like Sweden because, well, we would like to reuse this heat, and it really does make sense. The problem is with the financial perspective. If you are living in Sweden, like 90% of the year, you can sell it and it makes profit. In Southern Europe, it doesn't make sense at all. You just get rid of it as cheaply as possible. I don't know, build a pool or whatever, which will be even more warm than usual, and everybody is happy about that. We also considered, we even in PSNC, we had like a project with adsorption chiller. So maybe that's an idea. If you have a lot of heat, and in the summer you have like lots of high-grade heat, and the higher degree the temperature is, it's better. So maybe that's an idea, but when we tried to use directly the water from the HPC machine, the temperature was quite low. At least for the adsorption chiller, it was too low. So the temperature that we get, like the cooling was like, meh.
One thing that I would like to add, definitely location matters. What Andrzej said as well, size matters as well. So if suddenly you're too big, then it's becoming a problem. But overall, I don't think we should get like discouraged by the fact that, for example, part of that heat cannot be reused during summertime. Because during the winter time, the network can absorb any heat that you will be able to provide. So still looking, for example, someone mentioned at the beginning of the meeting about the EED requirements. EED obviously addresses the data centers and shows as one of the sources of waste heat, but essentially it addresses mostly the district heating operators that must decarbonize their network. That's the ultimate goal of what we're doing with energy efficiency. So in order to find the 1.2 gigawatt, as you said, of heat in Warsaw during winter time, we will need much more waste heat than just data centers. So just because we cannot reuse that heat during summertime doesn't mean we should not be doing it.
Okay, thanks. Okay, so you started already some comments about financial things, so we will move it in a moment. But maybe before, let's quickly comment our local use case. So let's imagine that we connect PSNC data center with nearby buildings of the University. Maybe, I don't know, through the connection is built by Veolia, maybe, or not, or maybe excess heat is given to Veolia. So what challenge, apart from like financial things and so on, what is the main challenge technically right now? Yeah, if you let's say we have it. Yeah. So what is the challenge to really make it working? Yeah.
To me?
Maybe I will just explain, yes, because you talk about the PUT. Yeah, we have a neighboring, quite large Poznań University of Technology campus with more or less 8 megawatt peak power, of course at minus 18 Celsius degrees. So during the average temperature with, for example, 3 to 5 Celsius degree in winter time, is more or less 3 megawatt heat demand, and PSNC constant production or constant use of electricity is more or less 2 megawatt. So it is quite a good case to try to, for example, supply with heat from PSNC the PUT, which is more or less low temperature sink. Yeah, because the temperatures are between 50, 55, 60 Celsius degree. in the winter time. And then in summertime, we think that we could transfer this excess heat from PSNC directly to Veolia when the temperatures in the summertime is 70 Celsius degree. Of course, what Andrzej said, the problem is that it's still an excess heat for you, so that's the problem. But technically, this PUT between data center and district heating is quite a good, let me say, accumulator, yeah, with much lower temperature than Veolia. So just a description of the case.
Okay, so the main challenge is less in technology, as we said before, but more in how to find a place for the heat in our production or consumption profile. Yes? So this is the main challenging point. Also, there is some points related to the data centers, but their way of business, so colocation services. So this is creating the period of cooperation and different period of yes, for maintenance and also for cooperation, because we are planning the plans for the 20-25 years. Data centers, I think that the period maybe for the building is the same, but for the servers, for the no.
It's like 5 to 10 years.
Yeah, so this could be also an obstacle building the business model. But for the case from here, I think that the best model is to use the prosumer model. And we are doing such a model in Warsaw. But I know that here in Poznań, at the moment, we don't have we haven't implemented yet. But I think in near future it is possible, and we can discuss and promote such solutions. But it will still consume our base load for the summer, these 2-4 megawatts, and adding to the system will replace our CHP production. Of course, this is small amount, but probably if you look at the Poznań city, there is a lot of such places which can apply. This solution can be applied. So I think that the importance of this situation is already addressed within the energy effectiveness directive, RED III directives, or other EU directives which are ongoing, or at the moment the heating and cooling strategy is being proceeded within EU. So I think there is a lot of strong policies over there. So we just need some time to implement into Polish regulations and create some financial incentives, create some investment grants, and make it in practice, not just in EU directives. So I think that this is near future, and we are facing it. I came back from huge conference in Międzyzdroje. It was 2 days ago. It is District Heating Operators Conference, and there was the main 2 words which were often within discussions: market coupling, sector coupling. So we need to create some strategies for coupling the markets, or coupling the sectors like data centers, like district heating operators, electricity operators and producers. And then I think we will find a solution how to combine the benefits and interest of each sector and find a win-win model. I know it is trivial, but I think that we should looking for such a solution.
And again, in Poland, I feel like we're at this early adopter stage, because other people have done it already, it works, and it proves that it can work. So I think we need these people who will actually commit to doing it, there will be obstacles, but who will commit to actually figuring out how to pass them. And we need first use cases to prove that the model works, and then the solution will actually scale. So that's why I'm also involved in heavily promoting the waste heat recovery from data centers. I mean, in Poland, we are operating second largest district heating network. So we really need to decarbonize that district heating network. And the data center is a great source of waste heat. So that's why I understand there's obstacles. The more I'm into it, the more obstacles there are, obviously. But the end goal is worth to overcoming these obstacles.
Yeah, and you you said about the decarbonization, which is crucial at the moment, and we are through the transformation process. And if we look at our CHP plant, we've got about 900 megawatts in coal-fired boilers. And to decarbonize it, what we should build. So it is not easy to decarbonize such a huge plant. So the easiest way, I think, is to make a decentralization, to make a small heat recovery plants, small data center, even reuse the heat, find a solution all over the district heating network, not at the one place at the CHP plant.
It doesn't have to be centralized. And there's one thing as well for the data center operators, because that's what I see as another asset of ours. I've been in many conversations with the Ministry of Climate and Energy, now Ministry of Energy, Climate and Environment, sorry, now Ministry of Energy. And during these work groups, everyone has seen electrification of district heating system as a challenge, because that's another huge cost that one has to bear to power those heat pumps. And then again, data centers are on the solution side of that problem, because we already have that power and we don't use it during winter time, because we operate extremely efficiently our cooling systems during winter time. So we have spare power capacity available that could feed the heat pumps. So overall, these two sectors are perfect for a couple. So we just need to figure out how to make that marriage happen.
Time. Question, okay.
We have question to the panel.
That's what I wanted to say now, yeah. Because we are drifting now to the financial and economic things, but yeah, I wanted to ask if there are any questions from
the problem is like the money is usually the core problem almost everywhere, because theoretically using, for example, solution removing like the normal air to water chillers with the adsorption chiller, we could be a consumer of the high-grade heat during the summer, because during the winter we cool it efficiently anyway, so we can sell or give away the heat during the winter, but consume the heat during the summer. That could be an option, but the question is, I guess, boils down if it does make sense from the financial and formal perspective. You can say, for example, that we are reducing the CO2 footprint, at least. Of course, it would be great if it makes also sense from the financial perspective, but there is an option, and like we can try to benefit from the fact that we are in between the north and south, and for some period of time we can consume, and some time we can produce.
Okay, so questions from the audience. Yeah, I thought that Lila from ZUTACOR will be there to comment on these temperatures, but I think she already left, right? Because she has a flight, and but okay. Your question.
Yeah, thank you very much. I was very happy listening to where the conversation was leading, yeah, because first you were saying you were showing the big picture, yeah, that you have, I don't know, 1,000 how many megawatt supply in the winter and or need, and then compared to this, the 30 megawatt is either too much or too little. This is the big picture, yeah, but we have a long network. I was speaking with the district heating company of Budapest, and I understood that this district heating network is has issues in certain parts. Yeah, so the further you go from the source, the heat source, some issues arise. I'm not an engineer and I did not understand, but probably, yeah, if you came to the distributed heating, and we don't necessarily have to speak about 30 MW. We don't have to solve the big picture, but locally there are issues that could be solved with 2-3 MW data centers. So what is your view on that? So are you proactively preparing a plan that I invite you here? So do you have such a plan or call to the data center community? And then another aspect is that it, of course, has to go hand in hand with the municipal spatial planning and energy strategies. How do you involve these actors? And is it possible, is there a force which could harmonize these interests of the data center, the problems to be solved on the district heating, and also the development of business, the building asset development in the city?
Question to me, as far as I understand. Yeah, so answering to the first question regarding the small sources built through the entire network. Yes, we are doing it, and we are decentralizing our CHP plant. So at the moment, for the moreover 1,000 megawatts, which is maximum demand of the network, we have installed, and almost everything in one place is our CHP plant, Caroline, named Caroline. When we were working on the decarbonization strategy, and within, I don't remember exact numbers, but within 10 years, more than 100 or even 200 megawatts will be distributed around this network. So this is the one reason that we are doing it is the better hydraulic parameters. We can reduce the temperature during the winter time. Other thing is the safety of the system, that we can, for example, during summer period, if there will be some problems with our CHP plant, we can source from the small distributed systems. During the summertime, it will be possible. So I mean, I think that these two reasons. So the hydraulic parameters will increase. We will reduce, or maybe more, reduce the temperature of the district heating system, and more or less the safety of the system, that we can source from the other plants, not only from one side. For the next
one issue, for example, in Poznań, it takes 24 hours to take from Caroline to the farthest point of the district heating. So okay. 24 hours. Yeah.
Caroline is the power plant.
Yeah. So if we have distributed, it will be.
Yes. If operator level up the temperature, it will come to yes, it will take 24 hours. And the second question, could you repeat, please?
I think it was about master planning, and if you don't mind, I would like to address that. Because yes, it's again the stakeholders and looking forward, right? That's what we need to get better at. And again, the Energy Efficiency Directive applies for all EU 27 countries. They all need to figure out how to reuse that waste heat. Again, Poland has second largest district heating network. The country that has the largest district heating network in Europe is Germany. And they have gone the farthest in implementing the law for reusing waste heat. There is a mandatory threshold of reusing waste heat, minimum 10% up to 20% in the future. I think you've discussed it. And the way they are looking at it, even if a data center is constructed outside of the reach of the district heating network, the current reach of the district heating network, they still require the data center to allow for future waste heat recovery. Because again, once the future districts are constructed around it, this could be used as a source of waste heat for future distributed sources. So I think this is a right way of looking at it, right? We should not only be solving the problems that we have today, right? We should also be looking forward, because then the assets that we have, like the data centers, could also provide for the future solutions.
Want to say something, Radek? Or? Oh. Okay, so just talking about, yes?
Is there a driving force that is assisting that your plans are harmonized? Yeah. So, and who is that? Municipality, national level, voivodeship. Where to look for that?
I think in the end it boils down to business, unfortunately, because we are all independent entities. We all run our own businesses, right? So it's a balance sheet, and it has to work, right? Unless there is an additional motivation from the government to actually make it happen. But like looking at the technical side of it, I believe the commercial aspect of it is just a goodwill of all sides and proper understanding of everyone's interest, right? We've been discussing recently that data center needs to recover the waste heat the most during summertime, because if you look at the other side of the waste heat recovery, that's a cold water that returns to your data center, right? So that way you're reducing your operating costs as well by reducing the load on your cooling system. So obviously our drive is to recover as much heat as we can possibly during summertime. The perspective of district heating operator is different. But I think, first of all, it's important to truly understand both sides of the picture, and then finding the right solution that works for both sides.
So the one information about the planning for the, maybe not the carbonization, but it is so, I don't know what is the English name of the document, but city is responsible for preparation of document, so-called plan for supplying of heat, gas, natural gas, and electricity. So municipal, they are responsible for the strategic planning, but sometimes it's just document which is issued, but no one is generally treating it as some direction. So there is no obligations within this document. This is just the information which was collected from the district heating operator, from the electricity operator, and the natural gas network operator. So this is simple information and some prediction about the consumption of these mediums.
And again, this is all about coupling, right? Because EED requires also this central heat reuse platform that would provide information about available waste heat sources. It's down to the local governments to implement these regulations and make it happen. If it will be just a paper document in some municipality, probably very little people will actually use it. But maybe we could use digital solutions for it and create a proper map of heat of Europe or a country or a region that would allow. It's all about streamlining the discussion between the two parties, and that's what we need to figure out, how to make these two talk together.
We are slightly behind the schedule, right? But I think okay. Another question from the audience. But I think.
Hello. So I am a quite technical person, a researcher at RISE in Sweden. So we were able to test the ZutaCore equipment, and some initial findings say that we have amount of heat and we have quality of heat. So we have electricity price, winter and summer. So what we noticed in the lab tests is we can increase the boiling temperature and the quality of heat significantly when we use less electricity. And I'm curious to hear your opinions about the quality and the amount of heat from you guys.
I'll answer first, if you don't mind, since I hold the mic. The quality, we differ obviously in opinions, but I think looking from the perspective of what's the second best alternative in terms of waste heat, I think data centers place very high. Whether it's 30 or whether it's 60, if it's 60, you're in perfect position. If it's 30, you're still very good. The quantity may become a challenge, as Andrzej said, right? If it's too much of heat, then it will still have to be extracted. It will not be able to be recovered fully. So it's a balance that depends on a specific application.
From our point of view, I think that both are important, but the quality is strictly regulated by the regulatory authorities. So they are responsible for the delivering of quality heat, and if there will be some discrepancy between the delivered heat and what was demanded or what was signed within the contract, we have to pay some fees. So our system is regulated based on quality and volumetric parameters. So both are important for us.
That's an important aspect. If the district heating operator doesn't deliver the quality, that's even a negative contribution to their bottom line. So, and from our perspective, how do we guarantee the quality of our waste heat? So you know, coupling that's the important.
And basically, it's kind of, we operate the data centers, but we don't generate the heat. It's our customers who do. So sometimes it's like, for the cloud environments, it's more or less stable. It's like you can, well, assume that it will be, the fluctuation won't be as high. But one of the challenges in HPC is like the bigger you are, the challenges are more significant, because we talked with like these large data centers, especially in US, when they have like the machines that have like 20, 30 megawatts, and they can spike from 0 to hero in 5 seconds. So I saw the discussion, the guy from PNNL, I guess it was, showed the discussion between the power plant and their center, that it's outrageous that you spike by 25 megawatts in 5 seconds. What do you think? It's like the network cannot handle it. So stop doing that. And they said, guys, it's not us, it's our customers. They require like the whole machine to do like simulation of some earth, like heat up or whatever. So the huge job. So it started in 5 seconds and the energy spiked, and everywhere on the network that was a warning, because I guess like the lines dimmed in the entire area. So from my perspective, I'm a little bit surprised you said we are a good source of the heat. Statistically, yes. But it may happen that we will do nasty things, and not because we want to do it, but that's the nature of, like, we just have a customer that runs some simulation or whatever. And sometimes it's better, sometimes it's worse. So that the energy, what we see, even with the full load of the machine, so the machine is, all the servers are occupied, the fluctuation is at least 30%. Even if that theoretically all the cores are occupied, the quality of the application may change like in a 30%. So it's difficult for me to guarantee, because I won't run any benchmarks or like stress tests just to like feel the power limits.
But it's electricity, not heat. Heat has a bit bigger inertia, yes? So
a
little bit.
What you've just said, and again, it boils down to communication, because you've just set your boundary conditions, and then you're saying, this is my world, that's how I operate, let's figure out how to reuse it, because then an engineering party in between has to figure out how to size that system to better match your profile, right? Because the answer is you will not be able to size it for 100% of your load, because it's just too unpredictable, right? But maybe there is, you know, you go into analyzing your profile and you find the right spot that could be reused.
Yeah, as I said, it's like less technical, more like a formal and like financial issue.
But you say you're not stable, yeah? But if we compare, for example, to industry, yeah, you work 24 hours, 365 days a year. And for example, if we compare with industry that they have a break during a weekend, yeah, or during a day. So, okay, if we compare with, for example, ground source heat pump, yeah,
it's less stable.
It's very stable, yeah. But if we compare to air is not stable at all.
We are coming to the point where we need to decide if you go for lunch or continue panel.
The floor is yours, Wojtek. Show us what are your results, how your tool is working, what are the capabilities of your model, and then we will listen also Sebastian and Karol.
Okay. Thank you, Attila, for the introduction. Hello, everyone. Today I'm gonna tell you a bit about CFD simulations we do at PSNC and the toolkit I'm developing in my PhD studies. By the way, my presentation is going to be mostly focused on air cooling in data centers, and in the following presentations, the liquid one is going to be developed more. So let's go to the agenda. At first, I planned a quick introduction to basics of air cooling in data centers. After that, I'll move to the, let's say, comparison of or maybe what CFD can offer us when we want to improve the efficiency of the cooling process in our data centers. After that, this is probably going to be the most interesting and colorful part, where I will show you examples of the CFD simulations we have done so far for our commercial partners. And at the end, I will describe a bit the toolkit I'm developing and what is the required input data and how it works. By the way, I didn't expect to be here so much CFD experts. So my presentation is designed in more lightweight. So sorry if plenty of information here is obvious for you. So let's start. Quick fact at the beginning, based on the data I found, currently the energy consumption of data centers worldwide is close to 1.5% of the global energy usage, total energy usage. In EU alone, this factor is a bit higher, it's closer to 3%. And this is not the end of the story, because it is estimated that by 2030, this power usage is going to triple. Right, but what about this energy which data centers are using? This is not only consumed by the IT equipment. There's also an overhead which is necessary to maintain the data center operational. For example, the cooling, power distribution, lighting, etc. So the average estimate, the average global estimate of the percentage that is of the energy which is used for cooling is close to 40%. On the left side, I've put the formula for well-known by you coefficient, PUE, which stands for power usage effectiveness. In short words, it gives us a clue what is the size of this overhead which data center needs. So for example, if an object has a PUE of 1.5, we know that the energy of the overhead is close to 50% of the energy used by the servers alone. The global average of PUE in 2024 was estimated to be 1.56, but as you have heard in previous presentations, it's easy to find objects with much better PUE value. And I also agree with previous presentations that PUE might not be the best KPI, but we still use it. Right now, we know several ways of heat rejection methods in data centers, and two main cooling media we use, air and some kind of liquid. For now, as AI-specialized data centers are growing in numbers, the first choice for such objects is liquid cooling. However, if we look globally on data centers, they are still vastly dominated by air cooling. So what are the advantages of this air cooling? This is a mature solution which was used for decades. It can be flexible, it's safe because there is no leakage of the fluid which could damage your IT hardware. Relatively low upfront cost. However, there is the limitation of the heat which it can dissipate. Because of relatively low specific heat of air, the upper limit, like estimated upper limit of application of this air cooling is close to 50 kilowatts per rack. Among this value, we need to use liquid cooling to be able to effectively dissipate the heat. So what is the role of air cooling in data centers? We need to basically keep two the most important parameters in, let's say, safe boundaries, the temperature and relative humidity. If we go out of these recommended ranges, we risk occurrence of unwanted phenomena which could limit the lifespan of our servers, or it can cause it overheating, so it will reduce the performance we get from them. But providing the proper conditions is just one part of the story. Another story is how to provide it effectively. So there, in air-based cooling, there can occur several airflow phenomena which are, let's say, the efficiency killers. For example, the first picture on the left upper one, air recirculation. This is the phenomena which occurs when the hot air from server exhaust moves directly back to the servers, which is not cooled by air conditioners, which reduces the effectiveness of heat dissipation, and many more, which you can see on the other pictures. But there exists plenty of solutions and approaches with which we can, let's say, fight with such phenomena. We distinguish two groups of actions. One is passive and second is active. Passive optimization is related to physical changes made in the data center. For example, we arrange servers or racks or air conditioners, and we separate hot and cold air masses so they won't mix. If we don't want to touch the physical setup, we also can act with active optimization, which is basically calibration or manipulation of the output parameters of air conditioners. However, among all these actions, the choice of the actions we apply is basically driven by the character of our data center. It was said before that each building is different. It is also valid for data centers. So, for example, if we want to physically change the setup in our data center, it requires turning them completely off. So it is very difficult for large objects. So probably it won't be the first choice. However, in larger objects, as there is more cooling devices, we get more flexibility in manipulating the output parameters. Right. So this is the background. Now let's focus on CFD itself and what can it give us in terms of analysis of data centers and the process of heat dissipation. Let's compare it briefly with just doing measurements. For example, if we do measurements with some devices, we get only limited data about what's going on in our object. It's like mostly point data get from the sensors. And this is not enough to get like a deep insight into phenomena which take place in the server room. So we are not able to identify any of the unwanted phenomena I have shown you earlier. What is more, if we stick just to measurements, if we come up with any solution how to improve the thermal situation in our data center, we cannot validate this solution before we actually apply it. So we take a risk when we change anything. On the other hand, if we use CFD simulation, we get a complete image of what's going on because we are simulating the whole volume of the air inside, which gives us opportunity to identify all the unwanted phenomena which are killing our efficiency of our cooling process. And the other advantage, big advantage, is that if we come up with some new solution, we can test it before application. So this is important from business and from business point of view and in terms of the risk we take. Now, the most colorful part. Now I will show you the examples of these CFD simulations which we as PSNC have done for our partners and investors which contacted with us. The first example is a mid-sized server room, which was at the stage of design. This is a server room contained in a container, and the investor wanted to check whether he wanted to select the setup of the cooling devices, because these were some unusual devices which allowed reversing the airflow in the cooling. So you could, on one hand, you could get the cold air from upper grills and from the bottom ones. So the investor wanted to check which setup is more optimal for his data center. And based on the model we created, we were able to give him a hint which is going to be more optimal in terms of the working conditions of the servers and efficiency of the cooling process. The next example, this is rather a small data center where the owner wanted to reduce the carbon footprint of the object. Here we decided to model it in more fine-grained way because the previous simulation, here we modeled each rack as a separate, like a single heat source, while here we modeled each server separately. This was highly non-homogeneous setup. By the way, the cooling facility was rather the office type. It wasn't like dedicated CRAC, for example, devices. These were like just regular split air conditioners we can find in our offices. Based on the suggestions of passive and as well as active optimization actions, we provided a solution for this partner based on which he could reduce both the energy consumption of this cooling facility and also to improve the working conditions of the servers. The third example, this is actually our former data center in our former building of PSNC, in which we had a headquarters like many years ago. There we had a problem with hotspots because our data center was also highly non-homogeneous. There was raised floor cooling, and we wanted to investigate several ideas of separation of hot and cold isles. And we, based on CFD simulations, we selected the best solution which could provide the best working conditions for our servers. Next example, you must have already seen this small room. This is our laboratory data center, where we analyzed the impact of the sun radiation, because one wall of the testbed data center is a glass window. So we decided to cover the window with PDLC foil to reduce this radiation impact, and we checked based on CFD how does it help with reducing this sun radiation, and how does it impact our setup and thermal situation. And the last example is more like an academic one. We wanted to provide a training set for machine learning algorithm. This was really simplistic setup with just 2 racks modeled as a single bodies with very simplistic, straightforward cooling airflow. And we wanted to multiply this simulation with manipulation of several chosen parameters. So at the end, we were able, thanks to the simplicity of the model and to HPC resources we were able to run over 3,000 of configurations with which we trained the model. These were, by the way, transient simulations. Okay, that's the end of the examples I wanted to show you. Now I'll move to the software we are developing right now. Based on the years of experience, we decided to automate the process of the CFD simulation preparation. All the know-how and experience we collected, we have put it into our framework. This is a framework written in Python, which is like a wrapper for OpenFOAM, which allows the user to automatically run all the workflow needed to perform CFD simulation for data center. We design it in a way which drastically simplifies the required input data. The user needs to prepare one main JSON file which consists of basic data I will show you on the next slide. And we wanted to create it in a way which doesn't require from the user to be an experienced engineer, because our software after the start of the execution performs like a thorough validation of the input, both logical and physical, and doesn't allow to proceed, especially to use HPC resources if it finds any wrong input, right? The software also includes editable model database with which the user can put references to the main input file and include models of specific IT hardware or air conditioning models into the domain. We also give the user the choice of a selection of the granularity of the modeling. As I said, we can model racks as single bodies or servers individually. And now I will go more into details in terms of required input data. So our framework can be run both on HPC resources and on local computer. The user needs to provide a Python environment and installation of OpenFOAM together with community packages, and he needs to, or she, to define a configuration JSON file in which there needs to be included several details of the environment. But this file needs to be just defined once, and we can forget about it. Now, so input data. As I said before, the main file, the JSON file, contains like the basic information about our data center, so like the dimensions and the devices which are included, their orientation, their location, like basic setup of output parameters. And this file contains references to the database, in which we include more detailed information about each device. For example, the location, size, and parameters of input and output surfaces, or like physical parameters of the device and its limitations. So as soon as the user provides the required input data, he can or she can execute our software with a single command line. Unfortunately, we don't have yet the GUI. However, we are working on it, and I hope we will deliver it soon in the future. And when formulating the command line, the user can also add some flags which control several options of the CFD workflow he realizes. For example, he can choose turbulence model, select if the analysis is static or transient, or whether to use compressibility or not, and plenty of more options. So yeah, this is like the basic information about the software I am currently developing in my PhD studies. And we reached the end of my presentation. So thank you for your attention. Here are the references to the information I included on the slide. So if you have any questions, I'll be glad to answer. I hope I didn't exceed the time.
Simulator. Hello. Actually, there is like something else, let's say, in bigger scale than like the CFD simulations. I'm not exactly bigger scale, but also the different scope, because Wojtek simulations are like mainly for the airflow and optimization of the usage of the cooling devices, yeah, and the setup of the room. And the tool that I am developing like serve the purpose for simulating, like, for example, whole data centers with taking into consideration like the energy usage, thermal usage, waste heat utilization. We can simulate like different scheduling algorithms. So I will try to go into a little bit more details, but let's treat me like a programmer, not like a specialist in like every dimension of the problems. So I want to talk about that the simulations are important. Simulation can provide you with a lot of profit, but I don't want to give any solutions today, because this is like not my field. There are experts that I want to support with my tool, not replace them. So yes, but the benefits of using the simulations mainly are like the first one is like zero risk of the system failure, because like we talked before, if I want to go today to the system administrator and tell that I have like this great idea, I mean, let's change the temperatures in whole system or change the scheduling algorithm, he will laugh me out and I can't like test it, or even worse, he lets me and something crashes and we've got like millions of loss, yeah? But with the help of the simulation tools, we can like check our ideas before we can actually apply them. So this brings us to the second point, where we can easily in the quick time compare like few different scenarios. For example, like some little parameter changes, and we can see how they affect, for example, our server room, not in just hours, but for example, in a whole year of, for example, energy consumption. And the third one that I included here, like the, for example, creating and running the simulations are like more expensive than, for example, buying new equipment and testing out if it will fit our expectations or our needs. So with that said, I will say a few words like how the tool works. So maybe to keep it simple, let's say that the user is like responsible for the two things. First one is to provide the input data, which is like the XML file, which includes like the structure of the data center. For example, let's say we have the data center that consists like of, I don't know, 100 racks, each one 32 nodes, something like that. There's like a lot of flexibility in here. And the other one is to provide the workload. So for example, define that we've got like few thousand of the tasks that needs to be computed on those resources from the previous step. And let's say it goes to the simulator, and for now let's treat it like the black box, and it gives us the results that we choose. For example, the energy usage of the nodes, like the thermal parameters, for example, like the temperatures on the CPUs, or I don't know, for example, we can calculate the waste heat that we are generating with our data center. And we can like compare with other resources, check if our idea is like correct, and could it like bring some benefits to our data center. But the main key in this simulator is that it allows the researchers to like write their own like plugins, which describes the behaviors of this, for example, for the nodes. Let's keep up with nodes. They don't need to know how the whole simulator works. They just need to provide those plugins, which are like simple Java codes that describes the behavior of the servers. For example, we've got the tasks that were listed, and we are writing the plugin for the energy usage, and it is for the user to like describe how this load level of the server is like converted to the power usage of the server. It can be data from the benchmark. It could be like I don't know, idea of some tweaking parameters. Basically anything you can like describe with some numerical like equation, and it goes along with some different parameters like the thermal usage of the components. For example, the reliability of the nodes, and some other policies. So like everything is up to the user, what they want to calculate and how. And we are just like providing the possibility. Okay, and few examples. And again, I'm not saying they are like good examples. I mean, I can't promise you profit from what I say right now, but I want to just say that we have to like have ideas, simulate them, and check if they are like correct or not. So, for example, using the simulation, we can check how our like different example. We've got our historical workload, for example, from our like server room, and we've got this Slurm scheduling system on it. We can like write the simulation describing our data center and our workload, and we can like check what will happen if we, for example, change the scheduling algorithm. For example, I will get to that once more later, but for example, we are considering like waste heat reusage, and we are connected to some building, and we want to check if we, for example, could schedule tasks that they are like prioritized and run, for example, in the day when there is like more need for the heat, and those who have like lower priority run at night, or I don't know when the heat is needed. The other example, we can like set up some restrictions. For example, we can check what will happen if we, for example, like set the level of the power usage that we don't want to exceed, or the temperatures that we don't want to like exceed on the processors, and we will work like with the different algorithms that will be turning down the frequency of the processors, so we can like save the energy, don't generate waste heat. But of course, this will like make the computation of the tasks longer. But this is like the case for some studies. Next examples, we can like simulate, as I said, different scheduling algorithms. For example, in one of the previous projects, we are like checking the algorithm of the other company that they wanted to like set different checkpointing frequency of the tasks that were running on the server, depending on the reliability of the server, which is like, for example, the possibility that the server will like crash in the duration of the application that is running on it. And for example, if the node is like super healthy, then we can like do these checkpoints like rather in some like bigger time steps than if the node is like failing. Or for example, if the node is failing, how quickly we can restore it from the previous checkpoint, or something like that. And the last example that I want to give you is this example that we were like talking about half of the day. So we were dealing with these scenarios that we want to calculate how much heat we are wasting in our building, and how we can provide like the connection to the campus outside, and the part on like our side, our server room, was simulated with this tool I was talking about. And then we were like checking those different scenarios. Like, for example, what could happen if we like increase the temperatures in our loop? Will it be like more efficient? Would it be like better heat? Yeah, for the campus. And this is the topic that will be continued by the Carol in the next presentation, because he was like simulating the campus part of it with another tool. Yeah, and I think for the simulation, for the presentation, it will be like everything.
I'm Karol Bandurski. I work here at Poznań University of Technology, but we have some cooperation with this place, with this group in the previous project. So it will be some experience with this project, but in true, I will base on very simple case, which is not directly this what we do there, but something more simply, hopefully also good for you. So the idea is to show you in true possibilities or sample of possibilities of TRNSYS software, which help to look on more comprehensively on the problem which we talk about today. So reuse of heat from data centers. So my plan is, I think, quite quickly show you the idea to use TRNSYS for coming from IT task to energy. Then talk a bit about the Renergetic project, which some new things which you didn't hear today yet, as this was let's say our first time when we work with TRNSYS in this context. Then present you this simply case of transferring IT to heat for building. And last slide, just to show you that this is just this simply case, but there are quite many things which we still can to do with TRNSYS, and I hope that in some days or next days we will do and present in papers or another projects. So what is TRNSYS? If you don't know, some of you, maybe somebody know, but maybe not all of you. So this is transient system simulation tool. It have quite good, quite big user forum, user group. There are some YouTube movies about that, some support on blogs. Quite nice Japan blog, but yeah. So this is a living tool. Still living tool, not free, but there is demo which you can play with this to understand better. This is very flexible tool. You can, if you know Fortran, you can develop your own modules for this tool. But if you don't know Fortran, but you know Python, there are plugins for Python, so you can integrate some Python models with TRNSYS models. To give you the example from another field, in Poland, last time we have some quite big project funded by National Center of Research and Development, where the idea is to create demonstrator of renewable energy sources heating source for some district in small city, and the part of this task was, before giving the opportunity and money, the funds to rise this plant, the starting teams need to create model in TRNSYS of this idea, of the concept, to prove that it will work. So the TRNSYS was used as a very good expertise tool to analyze technical potential of the ideas. Yeah, I have cooperation with Euros Energy, who was responsible and the general inventor of this demonstrator, which exists in the northeast of Poland, in one small city, Lidzbark Warmiński. Wolia, which we talk about today, which is a manager of district heating in Poznań, is also manager right now of this operator of this plant and this smaller district heating. So it is existing based mostly on renewable energy sources and heating plant in Poland. It operates more than a year. Okay, so this is what is TRNSYS. And TRNSYS was also used to many things because it is flexible, but one of those things is DC simulation. There was one project, European project a few years ago, Renew IT, which idea was to engage TRNSYS to these problems. The leading team which worked with TRNSYS was team from Barcelona. It was IREC, so I don't remember what the development of this abbreviation, but Institute of Energy, let's say, this kind of company, research and development company, and also more design company, Iguasol, and they work with TRNSYS in context of buildings, but in this project they work also with data center. And here you have two examples from their papers where they connect a data center by specific heat reuse solution, for example with swimming pool, or here also data center with the air cooling loop and water cooling loop and connection with the heat recovery in, I think, district heating. So they work with this problem in this software, so this is not very new. Yeah, but let's say as we talked today about the climate issue, they are from Spain, so maybe district heating issue was not so close to them, not so close like for us. And we start with the play with the TRNSYS from this project, which let's say already finished. It was an energetic project when we focus on the energy islands, so the islands, so the regions which can cooperate in energy, so transfer energy from one place to another. In one place the energy is the waste, and another is the need. So, and you see already this picture. So we have here the building which we are right now. Here is the road with the street, which is there, sorry, where you have the lake. Here you have the lake. The purple is the district heating pipes, which are underground, of course. Here is this the campus, the Poznań University campus, Poznań University of Technology campus. And there are a few buildings, as you see, they different in function. Sebastian showed you map where you see the function of these buildings, but here we can say that, for example, this building C is very low energy building. Radek say today you that the heating curve, maximum temperature of heating curve, so the temperature of water going to the heating system maximum is 35 Celsius degree. But for example, here you have not so low energy buildings. They are from 70s, so they are insulated, but still I think that heating curve is up to 70 or 80 Celsius degree. But for example, here you have quite nice buildings where is a lot of glass, and you can see from this place the cathedral, the old market, and so on. But because also because of that, the heating curve is almost up to 90 or something like this Celsius degree. So they different in not only the heating power needs, the heat consumption, but also the parameters, the quality of heat which they need. We talk about that today also. So the temperature which should be delivered to the heating system to give possibility of inside system to give the power, heating power to keep comfort condition. So this is the background of our start with TRNSYS. And here are two ideas how could be used the heat from this building, from this data center in our campus. So here you see that we have data center, so this place, and we can create the medium temperature internal, let's say, district heating network for campus, based on the heat pump, which rise temperature from cooling system of data center to the internal loop for campus, university campus. And if there are not enough, if campus is not use this energy, it is transferred to the district heating. It is one possibility. Of course, it is supported by renewable energy sources, PV panels on the roofs or another site, some battery and so on. And another possibility is to create low temperature. So here you have 55, and here is 22 Celsius degree loop for district or campus heating network. And the heat pumps is located for each building, and they provide dedicated temperature in each building according to their heating curve. Because here we assume that this heating is enough to keep the buildings, to give the buildings enough energy and enough temperature on the heating curve. So it means that maybe the building should be, let's say, refurbished, for example, or not all buildings could be supported with this system. Here we can dedicate. We are flexible to give the temperature in the building and the heating curve according to the building heating curve. And this is the idea which we try to develop in this project, but today I will not focus on them. They are quite complex and we are still thinking about them. But I would like to show you a very simple example and show the results and the possibilities of analysis and what could be done more with this. It is simple data center which transfer energy to the heating system of the building. Only heating system, no domestic hot water in this very simple case. So first you have data center where you define IT load. So this could be done, for example, by DC worms, like Sebastian said, and we use DC worms to generate such profile for energy, cooling energy from data center. But in this case, I do it in another way, also to show you the work of this another European project. Then you have heat pump. This is very important. I mean, thanks to the support from this Euro Energy, the company from which I mentioned before about this heating plant, they support us with characteristic of heat pumps, because as you know, heat pumps have quite complex characteristics. So it's not like gas boiler that you quite easily, let's say, can calculate how many heat you get from burning gas, or for example, even in the combined heating and energy devices, cogeneration. They are also sometimes maybe more complex, but it is not too hard to calculate how many energy and heat you get, electrical energy and heat get from the burning of the gas or other fuel. But in case of heat pumps, their performance, so how many electrical energy it consumes and how many cooling and heating energy deliver, it depends from the temperature and the flow of lower and upper heat source. So and it's changed a lot from based on those data. So to give you more precisely the explanation, there is a text file, quite big text file, which for different set of temperature and flows on lower and upper heat source give the performance of the heat pump. So to get such data from a company, from developer company, it's not so easy. So thanks to this cooperation, this Polish company producing also the heat pumps. We have this data, and it's possible to model this heat pump more precisely. And then we have a heating system. So we have heat exchanger, which where the heat for internal heating system for building is heated up, warmed up. What you can see here, so the heat from energy, so heat from data center is delivered to the storage. Heat pump this energy, this heat to the another storage where we will have higher temperature. From this storage, heat is delivered to this heat exchanger and give this heat to the internal heating system of building. Until this heat exchanger, we have glycol liquid inside these pipes, inside the cooling system and the heat pump. And in this part, we have water system. And additionally, you can see here auxiliary cooling device and auxiliary heating device. So it means that if the heat waste utilization, waste heating waste from data center is not enough the transfer from data center to the building is not enough to cool down the data center or heat up the building, we have supporting devices. And the idea of this example is to calculate how much electrical energy is needed for heat pump and how much additional cooling energy we need and heating energy we need, what is the cooling needs and heating needs additional besides the work done by heat pump. Yes, so the energy consumed by heat pump and energy needed, still needed to cool down data center and heat up the building. So this is our, let's say, performance indicators. This time, let's say in parallel to DC worms, I modeled this model, let's say, joined the IT task with energy. So we, based on this paper, which is from this previous project, which I mentioned on the beginning, they proposed there two type of IT load. So HPC, high performance computing, data tasks, and web task. And then for a given task, for let's say for hour of the week, they propose how look the load for a given tasks. We see that HPC and data are very similar, but the web is more based on the, let's say, human activity. So when there is night, so people don't use the web, and when they are up, they use much more. I'm not expert to say if it's close to the real schedules, but there are some logic behind that. So I think that it is based on some measurements done in this project. So, but this is the two types, and what's also very interesting for me, but for sure needs more analysis. They also give for IT load in percentage power consumption for a given type of load. Yes, so you can see that, for example, high performance computing is, let's say, most power consumption because it's reached 80% almost when we look on this approximation, yellow approximation, while the another type of tasks, so web and data, go below 70%. So it means that, if I understand, giving the same load of IT task, but different type, you will need less cooling for them to perform them. So this is, I use this approach in this simple example. And how also building was simulated in a very simple way. So I assume the heating needs of building, so gray line. So you have here ambient temperature, and if there is below 10 Celsius degree outside, it is mean average running mean from last 8 hours. The heating needs rise to to almost more than 40 kilowatts. Then blue and red line give you the view of the heating curve and the returning temperature. So supply temperature in the building heating system and return temperature in the same system. This assumption, how it could look like in some building. Okay, and then the simple task was to found how IT type and IT profile if influence on the performance indicators, how cooling temperature and flow influence on these performance indicators, and how influence also the heating curve, so building characteristics on these performance indicators. So IT profile we defined here. Temperature and flow in cooling system we define here. Yes, temperature the system is here. And the heating curve is defined, let's say, here. So here you have this reference case and another cases which was also analyzed. So this is general maximum power of the data center cooling, so 15 kilowatts. And in the reference case, we have 5 kilowatts per each type of load, so HPC, data, and web. The temperature supply and return temperature was 25, 28, so 3 Celsius degree difference. And in the building, we have maximum 50 kilowatts, the power, maximum power, and the heating curve in maximum points close to 80 and 70. And what was the difference between this reference case for another cases? So when we look on the modification of the IT load, we just move all IT loads to different types, so to HPC, to data, or only to web. So whole 15 was allocated only to one type of task, but other things are the same. So next, in the case when we look on the data center cooling modification, we change in temperature and flow through this cooling system. So we see here that here the temperature are raised, but the difference is the same. And here mean value is the same like in the reference case, but the difference is higher, so it means that flow is lower. So if we have to deliver the same cooling power and we increase the difference, so it means that the flow will be lower of this cooling liquid. And the last case, we modify the building heating system, so we just change the heating curve, so lower temperature in the heating curves, but the power of the heating system the same. So for example, higher area of the radiators in the building, yes, and give the possibility to decreasing the temperature. And what are the results? So here we have cooling needs, heating needs, electricity for heating pump, and remaining cooling and heating needs, which we have to cover by another systems. As you see, usually these two values are the same, like in reference case. Only here in IT load modification, they are different because we're changing task composition, so we get different cooling needs. But there are difference in some cases only. for these performance indicators. So we see that, for example, changing the type of task, that we get differences in electricity consumption for heat pump or cooling needs, but for this, let's say, the lowest consuming energy web task, this changes another. But then we have less energy for heating from heat pumps. Yes. So sorry. Maybe there is some water somewhere. Sorry. Yeah. Yes, and then when we modified cooling system, by making increasing the temperature of cooling system, we have decrease in consumption of heat pump and other systems. But changing flow is not influencing too much to the performance. Thanks. Thanks. Okay, thanks. And also when we look on the building modification, changing heating curve, we have quite high decrease in heat pump consumption, but another performance indicators have no too big difference. So this is just example to show possibilities. This is not universal solution, but showing the possibilities. And the last slide is to show that it is only the starting point, and there are much more possibilities in this software to do. So we can add. Now we look only on the space heating, but in true it will be to be really sensible. Let's say we should also consider domestic hot water, because domestic hot water is in every building, and also cooperation with district heating, as was shown in Energetic project we talked today that we sometimes maybe need to put some part of heat from data center to the heating system. Sorry, we can analyze here the influence of system elements, so storage tank, what is their volume, how it's influenced, temperatures, as we see in this example, topology of the system, as you see the mid and low temperature campus heating network. We can join also to this model renewable energy sources and the cooperation with this system. Cogeneration units also could be modeled there, so it will be connected in one model, and we can look on this cooperation. In this model, you see there was modules which was pumps, circulating pumps for this system, but I didn't plot and sum up the energy which is consumed by these pumps. But if we connect, for example, let's say the lower energy is building, the higher is share of the auxiliary system, the consumption of energy by auxiliary system like pumps or control. So, and also when we connect to the district heating, there are, we didn't talk about this today, but there are different temperature in the heating system, but there are also different pressure. And sometimes there are needs for some quite big pumps if we connect to this district heating with the data center cooling system. And these pumps are needed to keep this pressure, and it could be also quite big share of energy in such systems, so should be considered also. And this is possible in TRNSYS in some way. So all those things could be and will be analyzed for Warta campus simulation. So these two cases which I show you on the graphics. And also there is another one thing which we right now talking a bit about that together with Ariel and Piotr and others, that how cooling parameters influence on IT consumption and IT performance. So there is also some kind of interaction, yes, that IT load influence on the energy, but also parameters which parameters of cooling system also could influence on the IT or computing performance. So and this is this interaction, yeah, we hope to develop it more. So, but this is also nothing new, because some people, this is not our feature, yes, also look on that, yes. So temperature supply cooling temperature to the data center, the flow in this cooling system, and how it's influenced on IT consumption, energy consumption, and CPU average temperature. Yes, so it was analyzed, but yeah, but I think there is still possibility to develop and work for optimization. We hope. So this is all what I would like to present you today.
you.